The universe is an enormous, mysterious place filled with wonders beyond our imagination. From the tiniest particles to the vast, sprawling galaxies, it stretches far beyond what we can fully understand. Imagine floating through the calm expanse of space, drifting past countless stars, planets, and nebula, each one telling a unique story of creation. There are billions of galaxies, each home to millions, even billions of stars. These stars, along with their planets, form solar systems that drift through the vast stretches of the universe. And now, let us embark on a journey through space to explore the incredible wonders of the cosmos, from the familiar glow of the sun to the far-off unknown corners of the universe. The sun, a medium-sized yellow dwarf star, sits peacefully at the heart of our solar system. Its influence is beyond measure, providing light and warmth to our small blue planet. Imagine its soft golden light reaching across 93 million miles of space, touching everything it encounters. This light, created through nuclear fusion, is the source of life on Earth. As hydrogen atoms come together to form helium, they release an immense amount of energy, radiating warmth and light in all directions. This energy is essential to life on Earth. Plants absorb sunlight, turning it into chemical energy through photosynthesis, which in turn creates oxygen, the breath of life. Without the sun's gentle rays, Earth's temperatures would fall, oceans would freeze, and life would cease to exist. The sun's gravitational force, too, plays a vital role in keeping the solar system in balance. Its pull keeps the planets, including Earth, in their orbits, preventing them from drifting into the endless void of space. This pull also creates the cycle of seasons, as Earth orbits the Sun over the course of a year, bringing about changes in the environment that support the rich tapestry of life on Earth. The Sun also emits a constant stream of charged particles known as solar wind, which interacts with Earth's magnetic field. Sometimes this interaction creates beautiful phenomena, such as the auroras or northern and southern lights, which light up the night sky in shimmering colours. These cosmic displays remind us of the Sun's power and its deep connection to Earth's natural rhythms. The birth of our solar system began more than 4.5 billion years ago, in a vast cloud of gas and dust, a molecular cloud that formed the foundation of everything we know today. This cloud, made up primarily of hydrogen and helium with traces of heavier elements, was part of a nebula, a cosmic nursery where stars and planets are born. At some point, a disturbance, possibly caused by a nearby supernova explosion, caused the cloud to collapse under its own gravity. As it collapsed, it began to spin, and at the centre, a protostar began to form, our Sun. Around this newborn star, a disk of dust and gas flattened out, and through a process called accretion, particles began to stick together, forming larger clumps known as planetesimals. These planetesimals eventually grew into planets, moons, and other celestial bodies, each unique in its composition and characteristics. The inner regions of the disk, closer to the hot protostar, were too warm for gases to condense, so rocky and metallic materials formed the inner, terrestrial planets, Mercury, Venus, Earth, and Mars. Farther out, where it was cooler, gas giants like Jupiter and Saturn were able to form. These planets, composed mainly of hydrogen and helium, created an entirely different type of world. Beyond these gas giants, icy bodies and comets took shape, completing the diverse makeup of our solar system. From this cloud of gas and dust, our solar system was born, a vibrant and ever-changing system that continues to evolve and inspire awe in all who gaze upon it. Each planet in our solar system tells its own story, shaped by its unique composition and the conditions it experiences. Let's begin with Mercury, the closest planet to the Sun. Its rocky surface is bathed in extreme temperatures, so hot during the day that it could melt lead, and so cold at night that it could freeze air itself. Mercury has no atmosphere to regulate these temperatures, and its surface is pockmarked with craters, much like the Moon. Next we visit Venus, Earth's twin in size and structure, but with a much more hostile environment. Wrapped in thick clouds of sulfuric acid, Venus experiences surface temperatures hot enough to melt lead. Its atmosphere is a dense blanket of carbon dioxide, creating a runaway greenhouse effect that traps heat. Venus rotates in the opposite direction to most planets, causing the sun to rise in the west and set in the east. Earth, our home, is a unique gem in the vast universe. Here, life thrives thanks to a delicate balance of water, air and warmth from the sun. Our planet's climate system allows for a diversity of ecosystems, and its magnetic field protects us from harmful solar radiation, allowing life to flourish in ways that are still a wonder to us. Mars, the red planet, is a place of mystery and exploration. Known for its rusty, iron-rich soil, it holds the largest volcano in the solar system, Olympus Mons, and a canyon system, Valles Marineris, that dwarfs Earth's Grand Canyon. Although barren today, Mars has signs of ancient water flows, hinting at a time when it may have been capable of supporting life. The gas giants, like Jupiter and Saturn, are massive worlds made primarily of hydrogen and helium. Jupiter, the largest of all, is a swirling ball of gas with storms that have raged for centuries. Its Great Red Spot, a storm larger than Earth, has been observed for over 400 years. Saturn, with its magnificent rings, is a beauty to behold, a planet surrounded by icy particles that reflect the sun's light in a brilliant display. Farther out, Uranus and Neptune are ice giants, worlds bathed in blue and green hues due to methane in their atmospheres. Uranus spins on its side, causing unique seasonal changes, while Neptune experiences supersonic winds and dark storm spots that challenge our understanding of weather in space. Finally, Pluto, although reclassified as a dwarf planet, remains a captivating object of study. Its icy surface and heart-shaped glacier offer a glimpse into the far reaches of our solar system. Pluto's 5 moons, including the Large Charon, tell a story of an ancient world on the edge of our cosmic neighbourhood. These planets, with their distinct characteristics, each contribute to the grand story of our solar system. From rocky worlds like Earth and Mars to gas giants like Jupiter and Saturn, the diversity of planetary formation in our solar system is a testament to the creativity of the universe. As we move beyond our solar system, we are reminded that the universe is full of mysteries waiting for us to explore. From stars that burn brightly in the distance to galaxies that drift through the darkness, the cosmos offers an infinite array of wonders. And just as the sun's light has guided life on Earth, so too does the light of distant stars guide us in our quest for understanding. The universe is vast, and its mysteries are endless, but it's our curiosity, our desire to learn, that drives us to explore. Together, we journey into the stars, guided by the unknown, ready to discover what lies beyond. In the vastness of the cosmos, there are countless mysteries waiting to be discovered, each as unique as the stars themselves. From the smallest particles to the largest galaxies, space is a realm of endless wonder. As we drift through the universe, we encounter not only familiar celestial bodies, but also the unknown, awaiting exploration and understanding. One of the most fascinating objects in our cosmic neighbourhood is Titan, one of Saturn's moons. Titan stands out with its thick orange atmosphere, rich in nitrogen, much like the early Earth. Beneath this dense veil of gas, Titan holds a hidden world, with lakes and rivers flowing not with water, but with liquid methane and ethane. Imagine the eerie beauty of this frozen moon, with its icy surface and a secret ocean of water and ammonia lying beneath. Titan is a place of mystery and potential, where scientists believe the conditions might just allow for life, in forms we could only dream of. As we turn our gaze to Enceladus, another moon of Saturn, we find a world in motion, its icy surface hiding a dramatic secret. From the moon's southern pole, geysers erupt, sending plumes of water vapour, ice particles, and organic compounds into space. These plumes suggest a subsurface ocean beneath the moon's frozen crust, making Enceladus an exciting target for future missions that might one day reveal the mysteries of life beyond Earth. The materials from these geysers contribute to Saturn's E-ring, providing a unique opportunity to study potential habitats without ever touching the surface. Then there's Triton, a moon of Neptune, famous for its retrograde orbit, meaning it travels opposite to Neptune's rotation, suggesting that Triton may have been captured by the Neptune's gravity, rather than forming there. Triton's surface is a frozen mix of water and nitrogen ice, and it's pocked with mysterious cantaloupe-like terrain. Scientists are fascinated by its geysers, which eject nitrogen gas, hinting at subterranean activity. This combination of a strange orbit and surface activity makes Triton an intriguing subject in the study of captured celestial bodies. Between the orbits of Mars and Jupiter lies a fascinating region known as the asteroid belt. This collection of rocky bodies, ranging from tiny dust particles to massive asteroids hundreds of miles in diameter, plays a crucial role in our solar system. The belt is made up of leftover planetesimals, chunks of matter that never quite formed into planets. Its total mass is small, less than that of Earth's moon, yet it serves as a natural boundary, separating the inner rocky planets from the outer gas giants. The asteroid belt is also a cosmic reminder of the solar system's beginnings. It is believed to have formed from the primordial solar nebula, shaped by the immense gravity of Jupiter. But the asteroid belt isn't just a static collection of debris. It has also played a significant role in Earth's history. Occasionally, asteroids are nudged out of their orbits by Jupiter's gravity, sending them hurtling toward the inner solar system. These rogue asteroids have had profound effects on Earth, with one famous impact contributing to the extinction of the dinosaurs over 6 million years ago. Despite its role as a dividing line, the asteroid belt also holds valuable clues about the early solar system. Some of its largest inhabitants, like Ceres and Vesta, have been studied in great detail. Ceres, a dwarf planet, shows signs of water ice and potential cryovolcanism, hinting at complex processes beneath its icy surface. Vesta, on the other hand, has a differentiated structure, much like Earth's own, suggesting it once melted on the inside and underwent internal processes. The asteroid belt also serves as a potential resource for the future. Its objects contain valuable materials, including iron, nickel, and even water ice. The idea of asteroid mining has captured the imagination of scientists and entrepreneurs, offering the possibility of harvesting resources for long-term space exploration, reducing the need to transport materials from Earth. Comets, often called dirty snowballs, are some of the most captivating and mysterious objects in the solar system. Composed of ice, dust, and organic compounds, these cosmic wanderers come from the distant, icy regions of our solar system, mainly the Kuiper belt and the Oort cloud. As comets travel toward the Sun, they undergo dramatic transformations. The heat of the Sun causes their icy surfaces to sublimate, releasing gas and dust that forms a glowing coma around the nucleus, and often results in a brilliant tail stretching millions of miles into space. Comets are time capsules, preserving the ancient materials from the early solar system, and they provide us with valuable insights into the conditions that existed before the planets formed. These icy bodies have remained mostly unchanged for over 4.5 billion years, holding clues to the formation of the solar system and the building blocks of life itself. Some scientists believe comets played a crucial role in delivering water and organic molecules to the early Earth. This delivery system of essential compounds might have been critical in the emergence of life. Isotopic similarities between water in comets and Earth's oceans support this idea, suggesting that cometary impacts could have seeded our planet with the necessary ingredients for life. Beyond Neptune, the Kuiper belt marks the edge of the known solar system, containing thousands of icy bodies and dwarf planets like Pluto, Haumea, and Makemake. The Kuiper belt has been key in expanding our understanding of the solar system's outer regions, revealing a vast and complex neighborhood that extends far beyond the familiar planets. It offers clues about the early solar system, serving as a reservoir of objects that have remained largely unchanged since the solar system's formation. The Oort cloud, even farther out, is thought to be the source of long-period comets that travel through the solar system on elliptical orbits. Though no direct observations of the Oort cloud have been made due to its great distance, its existence is fundamental to understanding the origin of these comets. The Oort cloud, along with the Kuiper belt, marks the boundary between our solar system and the vast expanse of interstellar space, providing a glimpse into the ancient primordial material that shaped our cosmic neighborhood. In this peaceful journey through space, from the mysterious moons of Saturn to the icy bodies of the outer solar system, we begin to understand the complexity and beauty of the universe. Each celestial body, whether it's a frozen moon, a rocky asteroid, or a glowing comet, holds a unique place in the grand tapestry of the cosmos, contributing to the story of our solar system and the ongoing exploration of the stars. The mysteries of the universe are vast, but with each discovery we come closer to understanding the forces that have shaped us and everything around us. The journey continues, always unfolding, always reaching toward the stars. Far out in the cosmos, Pluto drifts in quiet solitude, far from the warmth of the sun. In 2015, our understanding of this distant world expanded as Pluto revealed its surprisingly varied surface. Vast plains of nitrogen ice stretch across its landscape, with towering mountains made of water ice rising gently from the surface. There's also evidence of recent geological activity, hinting at a dynamic, ever-changing world beneath the icy exterior. One particularly fascinating feature is Sputnik Planitia, a heart-shaped region thought to be a massive, slowly moving glacier made of nitrogen ice. Scientists believe this glacier sits within a basin, likely formed by an ancient impact, adding to the enigma of Pluto's past. Pluto's atmosphere, though thin, is equally remarkable. Composed mostly of nitrogen with traces of methane and carbon monoxide, it undergoes seasonal changes, expanding and contracting as Pluto moves through its elongated orbit around the Sun. During the closest approach to the Sun, the surface ice sublimates, replenishing the atmosphere, while it freezes back onto the surface as Pluto drifts farther away. These dynamic changes are a testament to the complex interactions between the surface and the atmosphere, even on distant small worlds like Pluto. Pluto's system of moons adds even more intrigue. Charon, Pluto's largest moon, is so substantial that the centre of mass between Pluto and Charon lies outside of Pluto itself, making it a binary system. Charon also has its own geological features, including a colossal canyon system and a dark reddish area at its north pole. This area, once named Mordor Mula, raises intriguing questions about tidal interactions between Pluto and Charon, suggesting a shared evolutionary history. The smaller moons, Styx, Nix, Ceres and Hydra, show chaotic rotations, likely influenced by the gravitational complexities of the Pluto-Charon system. Despite its extreme cold, Pluto tantalizes scientists with the possibility of chemical processes that could offer insights into fundamental organic chemistry. While it's unlikely that life as we know it exists there, the organic molecules detected on Pluto's surface, created by interactions between sunlight and cosmic rays with nitrogen and methane, are of great interest in the search for the building blocks of life in the solar system. Pluto's complex geology, atmosphere and fascinating moons continue to make it a subject of wonder, reminding us that even the smallest icy bodies can possess unexpected complexity. Now, let's move closer to the Sun, the mysterious world of Mercury, the innermost planet in our solar system. Mercury is a world of extremes, with temperature variations so dramatic they seem almost impossible. Without a substantial atmosphere to trap heat, the surface temperatures on Mercury can soar to nearly 800 degrees Celsius during the day, while at night they plunge to a chilling 330 degrees. This stark contrast highlights Mercury's exposure to the Sun's intense heat and its inability to hold on to warmth once the Sun retreats. Mercury's surface tells a tale of ancient geological history, marked by craters that tell of cataclysmic events. The Caloris Basin, one of the largest impact craters in the solar system, stretches over 960 miles in diameter. Surrounding this massive impact site are areas of chaotic terrain, thought to have been shaped by shock waves from the impact. Mercury also features vast plains believed to be ancient volcanic fields and towering cliffs, or scarps, some extending hundreds of miles long and rising more than a mile high. These scarps were likely created as Mercury cooled and contracted over billions of years, causing the crust to buckle and shift. At the heart of Mercury lies an unusually large iron-rich core, which makes up about 85% of the planet's radius. This core generates a magnetic field, although it is only about 1% as strong as Earth's. The presence of a magnetic field indicates that Mercury's core is at least partially molten, giving us clues about the planet's thermal evolution and magnetism. Mercury's orbital characteristics are also fascinating. It has a highly elliptical orbit, and it takes just 88 Earth days to complete one orbit around the Sun. But due to its unique spin-orbit resonance, Mercury rotates 3 times on its axis for every 2 orbits it completes. This results in an unusual day-night cycle, where one Mercury solar day, from one sunrise to the next, lasts about 86 Earth days. The combination of extreme temperature variations, a rich geological history, and peculiar orbital dynamics make Mercury a planet full of mystery, waiting for us to understand more about its past and present. Next, we journey to Venus, the hottest planet in our solar system. The intense heat on Venus is primarily caused by its runaway greenhouse effect. This phenomenon occurs when a planet's atmosphere contains an overwhelming amount of greenhouse gases, which trap heat and cause surface temperatures to soar. Venus's atmosphere is composed mainly of carbon dioxide, with thick clouds of sulfuric acid adding to its mystery. On Venus, solar radiation passes through its thick atmosphere and reaches the surface. The planet absorbs this solar energy, which is then re-emitted as infrared radiation. On Earth, some of this radiation escapes back into space, but on Venus, the dense carbon dioxide atmosphere traps the heat, creating a feedback loop that continually warms the planet. As the atmosphere heats up, it holds more heat, making the surface temperature rise even further. As a result, Venus has an average surface temperature of about 900 degrees, which is even hotter than Mercury, despite being farther from the Sun. The extreme pressure on Venus is another factor contributing to its scorching heat. The atmospheric pressure on Venus is about 92 times that of Earth's, and this pressure only adds to the trapped heat. The clouds of sulfuric acid reflect sunlight, preventing the surface from cooling down. This reflection ensures that heat gets distributed evenly throughout the atmosphere, creating a world that is both incredibly hot and hostile. What makes Venus particularly fascinating is that scientists believe it may have had a more temperate climate in its distant past, possibly even with liquid water on its surface. But over time, as the sun's radiation increased, it likely led to the evaporation of water, which then released more water vapor into the atmosphere, further intensifying the greenhouse effect. This runaway process transformed Venus into the fiery inferno we see today. Venus's extreme greenhouse effect serves as a stark warning about the power of greenhouse gases and the delicate balance required to maintain a habitable environment. Its story provides crucial insights into planetary climates and the forces that shape the conditions of a planet over time. Mars, often called the Red Planet, is a world full of geological wonders and signs of ancient water flows. One of the most notable features of Mars is Olympus Mons, the tallest volcano in the solar system, standing at a towering height of 13.6 miles, almost 3 times the height of Mount Everest. This massive shield volcano is thought to be formed by layers of lava that have accumulated over billions of years, making it a fascinating subject of study. Another extraordinary geological feature on Mars is Valles Marineris, a vast canyon system stretching over 2,500 miles long and reaching depths of 4 miles. This colossal rift is thought to have been formed by tectonic activity and the pulling apart of Mars's crust. The canyon system offers valuable clues about the planet's dynamic geological history and its past volcanic activity. Mars also holds signs of ancient water. Researchers have found evidence of outflow channels and valley networks, which suggest that liquid water once flowed across the planet's surface. Aris Vallis and Maedim Vallis are extensive channels that likely formed from catastrophic floods, while the presence of valley networks hints at a time when Mars may have had sustained surface water. These ancient waterways fuel speculation about the potential for past life on Mars, as liquid water is essential for life as we know it. Mars's polar ice caps are another area of interest, consisting of layers of water ice and carbon dioxide ice, also known as dry ice. These ice caps grow and recede with the changing seasons, providing direct evidence of Mars's climate changes over time. The chaotic terrain, characterized by randomly oriented blocks of rock, may have been caused by the melting of subsurface ice, adding another layer to the planet's intriguing geological history. Mars continues to be a captivating subject of study, offering essential clues about the planet's climatic past, volcanic history, and potential habitability. Its diverse landscape and the possibility of ancient life make it one of the most fascinating worlds in our solar system. Imagine a world so far away, a place filled with towering volcanoes, ancient river valleys, and mysterious chaotic terrains. This world is Mars, a planet that continues to captivate our imaginations. Every discovery, from its majestic landscapes to the signs of past water flows, brings us closer to understanding the possibility that Mars could have once supported life. The evidence we find enriches the grand story of our solar system, each new piece revealing more about the universe we inhabit. As we move through the vast reaches of space, we encounter Jupiter, the largest planet in our solar system. Its atmosphere is a swirling cauldron of gases, hydrogen, helium, ammonia, and more, where the iconic Great Red Spot continues to rage. This immense, persistent storm has been swirling for at least 350 years, maybe even longer, a testament to the dynamic processes that unfold in Jupiter's turbulent skies. The Great Red Spot isn't just a storm, it's a symbol of the power and beauty of the cosmos. Jupiter's rapid rotation, completing a full spin every 10 hours, generates powerful jet streams that create bands of clouds flowing in opposite directions. These bands of clouds form shear zones where gases violently clash, and it's in these zones that the Great Red Spot has been nurtured, spinning counterclockwise in the southern hemisphere. Unlike cyclones on Earth, which tend to weaken over time, Jupiter's Great Red Spot is fueled by energy from the planet's internal heat. This heat, which Jupiter radiates more of than it receives from the Sun, powers the convection currents that drive the storms and the wind patterns across the planet's surface. Despite its fierce appearance, the Great Red Spot remains remarkably stable. The storm's deep roots extend far below the cloud tops, possibly as deep as 200 miles into the atmosphere, which adds to its longevity. The storm's characteristic red colour is still somewhat of a mystery. Some believe it's caused by complex chemical reactions driven by solar ultraviolet radiation, mixing compounds like ammonium hydrosulfide and phosphorus. The colour can change over time, suggesting shifts in the storm's internal dynamics. It's one of the largest storms ever discovered, originally spanning over 25,000 miles across, large enough to fit 3 Earths side by side. Though the storm has been shrinking in recent decades, it still remains the largest storm in the solar system. Moving further into the mysteries of space, we arrive at Saturn, the planet with the most beautiful and distinctive rings in the solar system. These immense bright rings are made up of countless particles of ice and rock, varying in size from tiny grains to large boulders. Saturn's rings are unlike any others in the solar system, easily visible through small telescopes, their brightness and complexity setting Saturn apart from its fellow gas giants like Jupiter, Uranus, and Neptune. The rings are divided into several sections, each with its own unique characteristics. One of the most striking features of the rings is how they reflect sunlight, glowing with a soft, almost ethereal radiance when viewed from Earth. This brightness, caused by the ice particles that make up the rings, gives Saturn a dreamy, celestial appearance. The rings are not static. They change and evolve in response to the gravitational influence of Saturn's many moons, more than 80 moons to be precise. These moons play a crucial role in maintaining the shape of the rings, with some, like Prometheus and Pandora, shepherding the particles within the rings, keeping them in place. Their gravitational pull creates fascinating phenomena, like spiral density waves and bending waves, which travel through the ring particles, offering us a deeper understanding of the forces at play within Saturn's complex ring system. The origins of Saturn's rings remain a mystery, with theories suggesting they could have formed from the breakup of an icy moon, the disintegration of a comet, or the remnants of the primordial disk from which Saturn formed. What we do know is that Saturn's rings are relatively young, less than 100 million years old, and are expected to be transient, vanishing over geological timescales. Despite their temporary nature, Saturn's rings continue to captivate astronomers, offering a window into the fascinating processes that shape planetary systems. Now, let's visit Uranus, a planet so unusual that it seems to be a world set sideways. Uranus has an axial tilt of about 98 degrees, meaning it spins on its side unlike any other planet in our solar system. For about 42 Earth years, one pole of Uranus is plunged into darkness and freezing cold, while the other basks in continuous daylight. Then, as Uranus moves along its orbit, the poles gradually switch places, resulting in a dramatic exchange between deep winter and endless sunshine. Imagine the quiet stillness of the planet's shifting seasons, a world where light and darkness are in constant peaceful motion. The unusual tilt of Uranus is thought to have resulted from a massive collision with another planet-sized object early in its history. This impact likely knocked Uranus off its axis, leaving it with its current peculiar orientation. Uranus's extreme tilt sets the stage for fascinating weather patterns, with scientists speculating that these shifting seasons could stir up winds that reach supersonic speeds, creating complex cloud formations that could be visible from telescopes on Earth. Finally, let's travel to Neptune, the distant icy blue giant at the far edge of our solar system. Neptune's weather is some of the most violent in the solar system, with supersonic winds reaching speeds of over 1,300 miles per hour. These winds move faster than any hurricane or typhoon on Earth, creating a spectacular show of gas clouds and storm systems. Despite being so far from the Sun, Neptune's internal heat plays a key role in fueling these intense weather patterns, as the planet radiates more heat than it receives from the Sun. Neptune's internal heat, possibly coming from the slow compression of its fluid interior, helps drive convection currents in its atmosphere, creating the temperature differences that fuel the planet's fierce winds. The storm systems on Neptune, like the Great Dark Spot, are reminiscent of Jupiter's Great Red Spot, giving Neptune a striking resemblance to its larger neighbour. The mystery of Neptune's weather continues to intrigue scientists as they use observations from telescopes and the data collected from Voyager 2's flyby to unravel the forces at play within this distant, turbulent atmosphere. As we look beyond Neptune to the vast expanse of interstellar space, we are reminded of the incredible complexity and beauty of our solar system. From the icy moons of Saturn to the extreme weather patterns on Neptune, each planet and moon offers new insights into the forces that shape our universe. These discoveries, whether they come from the study of towering volcanoes on Mars or the mysterious storm systems on Jupiter, bring us closer to understanding the cosmos, revealing the secrets of the worlds that lie just beyond our reach. In the vast expanse of the universe, scientists have developed incredible ways to study planets that orbit stars light years away. These faraway planets, known as exoplanets, are a source of endless fascination. One of the most important methods scientists use to find these distant worlds is called the transit method. This method takes advantage of a very gentle and tiny dimming of a star's light as a planet passes in front of it. When this happens at regular intervals, it suggests the presence of an exoplanet. Thanks to powerful tools like NASA's Kepler Space Telescope, scientists have discovered thousands of exoplanets by observing these small changes in brightness. Another captivating approach is the radial velocity method, often known as the wobble method. As planets orbit their stars, their gravitational pull causes the stars to move ever so slightly. This gentle wobbling causes the light from the star to shift, moving towards the blue and red parts of the spectrum. By carefully tracking these shifts, astronomers can learn a lot about the planet's size and how far it is from its star. There is also a method called direct imaging. This is a bit more challenging since the light from stars is so much brighter than the light from their planets. But with advanced techniques like chronography, where the star's light is blocked out, scientists have been able to see the faint glow of exoplanets. Together, these methods create a beautiful and ever-expanding understanding of the universe, allowing us to learn about the size, composition, and even the atmosphere of distant planets. As each discovery is made, our knowledge of life beyond Earth grows, taking us closer to answering questions about the possibility of life elsewhere in the cosmos. Now, let's gently move into the heart of our own solar system, the Sun. The Sun is a radiant ball of energy, composed of different layers that work together in perfect harmony. At the core of the Sun, temperatures soar to around 15 million degrees Celsius, where nuclear fusion happens. This is the process where hydrogen atoms come together to form helium, releasing an incredible amount of energy in the form of light and heat. This energy travels very slowly, taking thousands to millions of years to journey outward through the Sun's layers. Once the energy leaves the core, it moves through the radiative zone, where it bounces around, absorbed and re-emitted by atoms. This slow zigzagging movement takes a long time, but eventually the energy reaches the convective zone. Here, hot plasma rises toward the sun's surface, cools, and then sinks back down, creating a boiling, turbulent environment, much like water simmering in a pot. Above this, we have the photosphere, which is the sun's visible surface. This layer is cooler than the core, around 500 degrees Celsius, and it's where sunlight finally escapes into space. On this surface, we can also see sunspots, cooler, darker areas caused by magnetic activity. Above the photosphere lies the chromosphere, which shines with a reddish glow during solar eclipses. Then out beyond that we reach the corona, the sun's outermost layer. Surprisingly, this part of the sun is much hotter than the layers below it, reaching temperatures in the millions of degrees. The corona is where the solar wind begins, a gentle stream of charged particles that flows from the sun and affects space weather. The sun's energy doesn't just light up our world, but it also impacts the entire solar system. This beautiful glowing force powers life on Earth and drives the processes that shape the solar system. The nuclear fusion happening deep inside the sun is the engine that drives its radiant glow. Here, hydrogen atoms collide and fuse together, creating helium and releasing energy in the process. This energy is what keeps the sun shining. But there's something even more profound that happens. This energy, over millions of years, contributes to the creation of heavier elements. Stars evolve over time, and in the process, they help create the elements that make up the planets and all life forms. As we look at the sun's sunspots, we notice something intriguing. Sunspots are areas on the sun's surface that are cooler than the rest, and they're often linked to bursts of solar energy, like solar flares. These sudden eruptions of energy send out waves of light, radio waves and high-energy particles into space. These solar flares can even cause changes in space weather, affecting satellite communications and navigation systems here on Earth. Beyond solar flares, the coronal mass ejections, CMEs, are even more substantial. These are massive bursts of plasma from the sun that, when directed towards Earth, can cause geomagnetic storms. These storms create stunning light shows in the sky known as the auroras, the northern and southern lights. These beautiful lights are created when charged particles from the sun interact with Earth's atmosphere, creating shimmering curtains of colour in the sky. While these solar events can cause disruption to modern technology, they also remind us of the cosmic beauty of the sun's energy. Each burst of solar activity contributes to the stunning displays of light, and even though they pose challenges to our technology, they offer a peaceful reminder of how connected we are to the sun and the universe. The solar cycle, a period of about 11 years, governs the sun's activity. It is during this cycle that we see changes in the intensity of solar phenomena, affecting everything from solar flares to the solar wind. As the sun goes through its phases of activity, it continues to influence space weather, reminding us of the gentle, ever-changing rhythms of the universe. Through all of these discoveries, we are continuously learning more about the universe's delicate balance. From distant exoplanets to the powerful energy of our own sun, every part of the cosmos adds to our understanding. We may not yet have all the answers, but each step we take into the unknown brings us closer to unraveling the beautiful mysteries of the universe. And as we drift through space, we are reminded of the quiet, constant dance of energy, light, and life that surrounds us. The sun, a warm and radiant ball of light, goes through a natural cycle that affects our space environment. About every 11 years, the sun's magnetic field flips, creating a cycle of activity known as the solar cycle. At the start of this cycle, when it is calm, the sun has very few sunspots and little solar activity. As the cycle moves forward, the sun becomes much more active. The number of sunspots increases, and solar flares and coronal mass ejections become more frequent. During this time, the sun seems to come alive, creating bursts of energy that can affect our technology on Earth. These solar flares can sometimes disturb satellite communications and even interfere with power systems. The coronal mass ejections, which are massive bursts of the sun's plasma, can create storms in space when they interact with Earth's protective magnetic field. These storms can be risky for satellites, and astronauts in space, as well as those on flights over the poles, may experience increased radiation. This solar cycle not only impacts technology, but also affects the weather in space, gently guiding the dynamics of our solar system. The sun's influence reaches far beyond just Earth. For instance, when the sun is more active, the outer atmosphere of Earth expands. This causes satellites to move slightly in their orbits, requiring adjustments. The sun's activity also affects how much ultraviolet and X-ray radiation reaches Earth, which can, in turn, affect the ozone layer, helping us understand more about the ever-changing environment around us. Luckily, with advancements in technology, scientists are now better equipped to predict and prepare for these solar changes. Space observatories like NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory allow scientists to monitor the sun's activities closely. These observatories provide a clearer view of the sun's behavior, helping us protect our technology on Earth and stay safe from solar storms. In addition to these powerful solar observatories, spacecraft like the Parker Solar Probe and the Solar Orbiter venture closer to the Sun, gathering important information about its outer layers. These missions are designed to answer some of the Sun's greatest mysteries. They help us learn more about solar wind, the Sun's magnetic fields, and how these processes affect not only Earth but the entire solar system. The knowledge from these space missions is helping scientists create a clearer picture of solar activity, which helps us prepare for the future. Now, let's drift closer to the Moon, our closest celestial companion. The Moon goes through a beautiful dance of light and shadow, changing its shape as it orbits Earth. Every 29.5 days, the Moon completes a cycle called a lunation. This cycle is a delicate interaction between the positions of the Earth, the Moon and the Sun, with different parts of the Moon's surface becoming visible to us. It begins with the new Moon, when the Moon is between Earth and the Sun. During this phase, the side of the Moon we can't see is completely in shadow, so it disappears from the night sky. As the days pass, the Moon moves into the waxing crescent phase, where a small sliver of light begins to shine. Each night the crescent grows a little bigger, until it becomes a half moon during the first quarter phase. The light grows fuller until we reach the full moon, where the entire illuminated side of the Moon is visible, bright and shining in the night sky. After the full moon, the light starts to fade, moving into the waning gibbous phase. The Moon then passes through another half-moon phase called the last quarter, with the opposite side lit up compared to the first quarter. Finally, the Moon begins to shrink back into a waning crescent, gradually disappearing until the cycle begins again. These phases are caused by the angle at which we view the Moon, and the constant changes provide a soothing rhythm in the night sky. People have long used the Moon's phases to keep track of time, and understanding them helps us appreciate the slow, steady movement of the stars and planets above. The Moon's origin has fascinated scientists for many years, and the most popular theory is the giant impact hypothesis. Around 4.5 billion years ago, a massive object named Theia collided with the young Earth, sending debris into space. This debris eventually came together to form the Moon. The Moon's composition is very similar to Earth's, suggesting they share a common origin. Other theories, such as the capture theory or the fission theory, were considered at one point, but they didn't explain the similarities between Earth and the Moon, as well as the giant impact theory does. Some researchers now believe that several impacts may have contributed to the Moon's formation. As we explore the Moon's surface, we see a rich tapestry of geological features. Lunar maria, or seas, are vast, dark plains formed by ancient volcanic activity. These areas are not filled with water, but are solid basaltic plains. You can see them with the naked eye as dark patches on the Moon's surface. The lunar highlands, which are lighter in colour, are filled with craters, a reminder of the Moon's violent past. The largest crater, the South Pole Aitken Basin, is a massive impact structure, more than 2,500 kilometres across. It's one of the largest and deepest craters in the entire solar system. The Moon's surface, with its maria and highlands, tells the story of billions of years of cosmic activity and planetary evolution. Every crater, every plain adds a new layer to our understanding of the Moon's history. Just as the Sun's activity affects us here on Earth, so does the Moon's quiet, constant presence above us. It affects tides and rhythms, pulling at the oceans and subtly influencing life here on Earth. The dance between the Earth, the Sun, and the Moon is a beautiful reminder of the calm forces that keep our world in balance, just as the Moon's surface continues to reveal the ancient stories of the cosmos. As we look to the stars and the endless sky above, we are reminded of the delicate cosmic balance that governs everything in our universe. The sun's cycles, the moon's phases, and the planet's motions all weave together, creating a steady rhythmic flow that has been shaping our universe for billions of years. Let's rest now, knowing that as we sleep, these celestial bodies continue their quiet dance, lighting up the skies and guiding us gently through the night. The moon's surface is a silent storyteller, revealing the history of a world shaped by cosmic events and ancient forces. Its lunar maria, or seas, are vast, dark plains, formed by ancient volcanic eruptions. Although these seas are not filled with water, they stretch across the surface in dark, beautiful patterns, created when molten lava solidified billions of years ago. These ancient lava flows created smooth basaltic plains, now known as the maria, that contrast with the lighter lunar highlands, the oldest parts of the moon's surface, filled with craters from countless impacts. As we look closely, we see scarps, cliff-like features that hint at the moon's interior slowly cooling and contracting over time. These scarps, like the ones in a place called Rimae Erecta, are reminders that the moon, although calm and quiet, still carries the memory of deep changes. Even though the moon doesn't have active tectonic plates like Earth, these scarps show that its surface is still shifting, cracked by slow internal forces. Covering the moon is a layer of regolith, fine dust, and fragmented rock created over billions of years by tiny particles from space. This powdery dust, soft and fine, blankets the solid rock beneath it, forming a landscape of stark beauty and mystery. It's the result of countless micrometeoroid impacts, each one leaving a small mark on the surface of the moon, a record of the universe's gentle but persistent forces. The moon also plays a crucial role in life on Earth. Its gravitational pull creates tides, the rising and falling of the oceans, which rhythmically wash over the shores twice a day. You can picture Earth as a big ball of water, with the moon's gentle tug pulling on it, creating bulges of water on the side facing it. As Earth spins, different places pass through these bulges, experiencing high and low tides. This rhythm created by the moon's pull helps mix ocean waters, distributing nutrients and supporting marine life. The sun also has a role in this dance, pulling on Earth's waters too. When the sun, Earth, and moon line up, like during full moons or new moons, the gravitational pull is stronger, creating spring tides, where high tides are higher and low tides are lower. When the sun and moon are at right angles to each other, as during the first and third quarters, their pull weakens, resulting in neap tides, where the difference between high and low tides is smaller. These tidal movements aren't just important for marine life, they also influence human life, helping us with navigation, fishing, and even shaping how we live near the coast. Over time, this pull from the moon has slowly slowed Earth's spin, lengthening our days ever so gradually. It's a quiet, constant force that connects us to the moon in ways we might not always notice, but which have profound effects on our planet. One of the most remarkable chapters in our understanding of the moon comes from the Apollo missions, which spanned from 1969 to 1972. These missions provided a treasure trove of insights, especially from the lunar rocks and soil samples brought back to Earth. These samples told us that the moon's composition is similar to Earth's mantle, supporting the idea that the moon was formed after a massive collision between Earth and another body. The samples revealed that the moon's surface was shaped by both volcanic activity and impacts from space, showing how the moon has evolved over billions of years. During the Apollo missions, astronauts also deployed scientific instruments, conducted experiments, and collected samples from different areas on the moon. They found evidence of volcanic activity and learned that the moon's surface has been shaped by both internal forces and external bombardments from meteoroids and asteroids. Some of the most surprising discoveries were moonquakes, which suggested that the moon has a layered interior, like Earth, with a crust, mantle, and small core. The legacy of Apollo still influences lunar exploration today. The technologies developed for those missions set the stage for modern exploration, leading to initiatives like NASA's Artemis program, which plans to return humans to the Moon. Artemis will not only bring astronauts back to the Moon, but aims to establish a permanent presence there. The knowledge and experience gained from Apollo missions serve as guiding beacons for future lunar exploration. These missions not only proved the power of human ingenuity, but also cemented our place in the cosmos, showing that exploration can provide profound insights and change the world. The future of human exploration and the colonization of the Moon is becoming an exciting reality, with new technologies and global cooperation paving the way. One of the most exciting new programs is NASA's Artemis, which plans to return humans to the Moon by 2024. The program also envisions a sustainable human presence by the end of the decade, making the Moon a stepping stone for deeper space exploration, like missions to Mars. Artemis, starting with an uncrewed mission to test new rockets and spacecraft, will progressively lead to landing astronauts on the Moon's south pole, a region rich in scientific potential, including water ice. International collaboration is also an important part of this new era of lunar exploration. Agencies like the European Space Agency, ESA, Russia's Roscosmos, and China's CNSA have all planned missions to the Moon, contributing to the shared goals of scientific discovery. Together, these missions will build a sustainable human presence on the Moon, laying the groundwork for future space exploration. Technology plays a crucial role in these missions, especially in utilizing the Moon's resources. For example, extracting water from lunar ice will be essential for producing oxygen and fuel to support lunar bases and future space missions. This is part of a broader plan to establish infrastructure on the Moon that can protect astronauts from extreme temperatures and harmful solar radiation. 3D printing technology might even be used to build habitats using lunar regolith, the Moon's surface material. Private companies like SpaceX and Blue Origin are also key players in this vision for the Moon. SpaceX Starship aims to transport crew and cargo to the Moon, reducing costs and enabling more missions. Blue Origin's Blue Moon lander will help deliver supplies to support the broader goals of lunar colonization. These collective efforts are transforming the Moon into a hub for scientific research and technological innovation, with the goal of enabling deeper space exploration. Establishing a human presence on the Moon will offer invaluable experience, helping humanity learn how to live and work in extraterrestrial environments, preparing for the challenges of a multiplanetary future. As we look to the stars, we are reminded of the Moon's role as our closest companion in the cosmos. Its presence influences life on Earth in ways both subtle and profound. By exploring the Moon, we continue to unlock the mysteries of the universe and prepare ourselves for the next great leap into the stars. The stars, in their vast diversity, have stories to tell, each one adding a piece to the grand cosmic narrative. They shine brightly in the sky, from the smallest, most enduring red dwarfs to the magnificent colossal blue supergiants. At the far end of this stellar spectrum are the red dwarfs, small yet abundant stars that are cooler than our sun. Their glow is a soft reddish light, and because they burn their fuel so slowly, they can live for trillions of years, far outlasting many of the stars we are familiar with. Their quiet, enduring presence adds a gentle, steady light to the cosmos, a symbol of energy that stretches across time. In contrast, the blue giants and the blue supergiants, such as Rigel in the Orion constellation, burn brightly but quickly. Their blue light is intense, and their lifespan is much shorter, burning through their fuel in a matter of millions of years. When these stars near the end of their life, they explode in supernovae, an event so powerful that it can outshine an entire galaxy for a short period of time. These explosions scatter rich elements like iron and oxygen into the space around them, seeds for future stars and planets. But supernovae are not just destructive, they are also the creators of new life in the universe. As a supernova releases its energy, it creates waves that push against the surrounding gas clouds, compressing them and creating new regions where stars can form. This cycle of death and rebirth is a constant, ensuring that new stars are always born to light up the universe. One of the most fascinating outcomes of a massive star's death is the black hole. A black hole is formed when a star collapses under its own gravity, creating a region where the pull is so strong that not even light can escape. These dark, mysterious objects are surrounded by an event horizon, a boundary beyond which nothing can return. Despite their fearsome reputation, black holes play a crucial role in the universe. They help shape galaxies and warp space-time, influencing the paths of nearby stars and even altering the structure of entire galaxies. In the cosmic dance of stars, binary star systems offer a beautiful, complex performance. In these systems, two stars orbit around a common centre of mass. They move together in a rhythmic pattern, their gravitational pull on each other creating a delicate balance. This unique interaction can lead to some fascinating changes. For example, a red giant may share its outer layers with a smaller companion, turning into a white dwarf. In certain cases, this interaction can even trigger a nova, a brilliant flash of light as the material ignites. These systems provide astronomers with a natural laboratory where they can observe how stars evolve and change over time, revealing secrets about their mass, life cycle, and behaviour. The Cygnus X1 system, which contains a stellar mass black hole, is one of the most well-known examples of this. As the black hole pulls material from its companion star, it creates a disk of gas that shines brightly with X-rays, detectable from Earth. It's a remarkable reminder that even in the darkest parts of space, there is energy, life, and movement. Among the many ways we look to the stars, constellations are perhaps the most familiar. These patterns of stars have been named and mapped by humanity for millennia. They have served as guides, helping ancient travellers navigate the night skies. Constellations were not clusters of stars bound together, but rather a way to group the stars based on their positions as seen from Earth. The stars themselves may be light years apart, but from our vantage point, they appear to form beautiful, meaningful patterns. The Big Dipper, part of the constellation Ursa Major, has been a guide for sailors, helping them find their way across oceans. Farmers too have looked to the stars, using the changing positions of constellations to know when it was time to plant or harvest crops. Constellations were not only a practical tool, but also an integral part of cultural and religious practices across the world. They marked the seasons, told stories, and connected communities to the sky above. These star patterns are more than just a tool, they are a canvas, painted by countless cultures, each adding their own stories, myths, and legends. Constellations like Orion, with its bright stars, have inspired countless tales of mighty hunters and celestial warriors. The stories told by the stars are as old as humanity itself, carrying with them the wisdom and wonder of the ages. As we turn our gaze from the stars above us to the moon that orbits our planet, we see another dance of celestial bodies. The moon, with its surface of dark Maria and light highlands, has long been a source of fascination. Its surface is marked by craters, scars from eons of impact, and its age-old landscape tells the story of a moon shaped by time and forces beyond our understanding. The Maria, large dark plains created by volcanic activity, contrast sharply with the lighter, heavily cratered highlands, which are the oldest parts of the moon's surface. But it is the moon's role in Earth's rhythm that makes it so significant. The tidal forces it creates on Earth's oceans cause the water levels to rise and fall, creating the gentle rise and fall of the tides. This rhythmic dance, known as the tidal bulge, is a result of the moon's gravitational pull on Earth's waters. As Earth rotates, different parts of the planet pass through these bulges, experiencing high and low tides twice a day. The sun, too, plays a part in this celestial rhythm, affecting the tides. When the sun, moon, and Earth align, like during a full moon or new moon, their combined gravitational forces produce spring tides, where the high tides are higher and the low tides lower. When the sun and moon are at right angles, the tides are less extreme, known as neap tides. This subtle interplay of forces shapes life on Earth, affecting everything from the mixing of ocean waters to the way we live our lives. The moon's influence on Earth, however, is not limited to its effect on the tides. Throughout history, it has guided humans on their journeys, helped farmers track the seasons, and served as a symbol in countless cultures. The Apollo missions, which brought humans to the moon between 1969 and 1972, provided invaluable insights into the moon's surface and its geological history. The astronauts who ventured there brought back rock samples that told the story of the moon's origins, confirming the theory that the moon formed from a giant impact with the Earth billions of years ago. The Artemis program continues this journey, aiming to return humans to the moon and establish a sustainable presence there. The moon, once a distant dream, is now becoming a hub for scientific research and exploration, with new missions and technologies opening the door to a deeper understanding of the cosmos. The moon, with its quiet beauty and powerful influence, reminds us that we are all part of a vast interconnected universe, where even the smallest movements, whether of stars, planets, or the gentle pull of the moon, create ripples that shape the world around us. And as we continue to explore the stars, the moon will always be there, guiding us, a constant companion on our cosmic journey. In the vast expanse of the night sky, constellations serve as a bridge between our world and the cosmos, offering a peaceful and comforting presence as they guide our understanding of the universe. For thousands of years, humans have looked up at the stars and created stories about them. Ancient civilizations like the Greeks crafted myths of gods, heroes, and mythical creatures, immortalizing these tales in the stars. Among these stories is Orion, the mighty hunter, and his loyal companions, Kint Major and Kint Minor, who are forever chasing the celestial Lepus. These celestial stories not only brought meaning to the sky, but they also helped humans navigate through the darkness, connecting them to the rhythms of the universe. Over time, astronomers defined 88 constellations, giving each a clear boundary, making the stars easier to observe. The International Astronomical Union, IAU, formalized these boundaries in the 20th century, ensuring each part of the sky belongs to a particular constellation. While constellations continue to captivate our imagination, they also serve an educational purpose. They help scientists locate stars, nebulae, and galaxies. More than just visual symbols, these constellations embody our innate desire to understand and find meaning in the cosmos. Among the vast tapestry of stars, a few constellations stand out, both for their beautiful patterns and the rich myths that surround them. One such constellation is Orion, easily recognized by the 3 stars that form his belt. In Greek mythology, Orion was known as a mighty hunter, admired by the gods for his handsomeness and skills. However, his heroism led to his tragic end, either by the sting of a giant scorpion, which is now represented by the constellation Scorpius, or through other mythic tales of divine retribution. Despite the varying stories, the heroic legacy of Orion continues to shine brightly in the sky, captivating stargazers all around the world. Another well-known constellation is Ursa Major, more commonly called the Big Dipper. In the Northern Hemisphere, these 7 bright stars form part of a larger pattern that resembles a great bear. Native American cultures often see the Big Dipper as a celestial bear, pursued by 3 hunters. In Greek mythology, Ursa Major represents Callisto, a nymph who was turned into a bear by the jealous goddess Hera. Eventually she was placed among the stars by Zeus, and her son Arcas became Ursa Minor, or the Little Bear. These constellations remind us of transformation and the strength of familial bonds. Then there is Cepheus, with its distinctive two-shape. This constellation tells the story of a queen named Cassiopeia, whose vanity led to her downfall. She boasted that her beauty surpassed even that of the sea nymphs, angering Poseidon, the god of the sea. In retribution, Poseidon condemned Cassiopeia to the night sky, forever spinning on her throne, often appearing upside down, a reminder of her arrogance. These constellations, along with others like Pegasus, Andromeda, and Leo, weave a rich tapestry of stories blending culture, nature, and humanity's timeless desire to understand the world above us. They continue to inspire awe, and they offer an enduring legacy that brings the cosmos closer to us, both in the realm of astronomy and mythology. The Milky Way, our cosmic home, stretches across the night sky as a magnificent spiral of stars, gas, dust, and dark matter. At the centre of this galaxy lies the galactic core, a dense and tumultuous region dominated by a supermassive black hole known as Sagittarius A, weighing about 4 million times more than our Sun. Surrounding this powerful center is the galactic bulge, a spherical collection of older stars and star clusters that stretches for thousands of light years. The spiral arms of the Milky Way extend from the bulge, sweeping gracefully across the sky. Our solar system resides in the Orion Arm, a minor spiral arm positioned between the larger Perseus and Sagittarius arms. These arms are home to young luminous stars and vast clouds of gas and dust, creating a glittering backdrop of star nurseries and nebulae. The spiral shape of the galaxy is maintained by density waves that compress gas, triggering new star formation as they move through space. Beyond the spiral arms lies the galactic disk, a thin, rotationally flattened plane that holds the majority of the stars and nebulae in the galaxy. Surrounding this disk is the galactic halo, a vast and diffuse area filled with ancient stars and globular clusters, some of the oldest objects known in the universe. The halo is thought to be rich in dark matter, a mysterious substance that exerts gravitational forces but emits no light. Dark matter influences the galaxy's mass and its rotation, though it remains largely unseen. The outer reaches of the Milky Way are a more sparsely populated expanse, where solitary stars and faint streams of stars, remnants of past galactic mergers, wander. These quiet regions tell the story of the galaxy's evolution, shaped by interactions with other galaxies over billions of years. When we think about galaxies, we recognize their colossal size and variety. The Milky Way is just one of many, and these majestic structures are divided into three primary types: spiral, elliptical, and irregular. Each type offers a unique insight into the processes of cosmic formation and evolution. Spiral galaxies like the Milky Way are the most visually striking, with their elegant arms spiraling outward from a central bulge. These arms are home to regions of intense star formation, where young, hot blue stars shine brightly, illuminating the galaxy. Some spiral galaxies are further classified as barred or unbarred, depending on whether a bar-like structure of stars cuts through the central bulge. In contrast, elliptical galaxies have a more uniform, oval shape and lack the complex arms seen in spirals. They are often populated by older red stars, and their structure suggests they have exhausted much of their interstellar gas, leaving minimal material for new star formation. Elliptical galaxies are believed to form through the collision and merger of smaller galaxies, resulting in their more homogeneous appearance. Irregular galaxies deviate from these orderly schemes and lack a defined shape. Often smaller than spiral and elliptical galaxies, they appear chaotic, with regions of active star formation scattered among older stars. Their irregularity is often the result of gravitational interactions with nearby galaxies or remnants of past galactic collisions. Among these many galaxies, some stand out for their immense size. One of the largest known galaxies is IC 1101, a massive elliptical galaxy located over 1 billion light-years away in the constellation Virgo. IC 1101 spans an astonishing 1 million light-years across, about 60 times the diameter of the Milky Way. This enormous galaxy is home to hundreds of trillions of stars, many of which are old and red, indicating that active star formation has long since ceased. Another colossal galaxy is ESO 30617, located about 500 million light-years away. While not as large as IC 1101, it still stretches over 1 million light-years in diameter. These giants, with their vast number of globular clusters, offer a glimpse into the complex and often violent histories of galaxy formation. The study of these cosmic giants helps astronomers understand the growth mechanisms of galaxies. By exploring these massive structures, scientists gain insights into how galaxies evolve, merge, and form the intricate fabric of the universe. As we look up at the night sky, we are reminded of the endless wonder that the universe offers. From constellations steeped in myth to galaxies that stretch beyond our comprehension, the cosmos is a vast and ever-evolving tapestry. Each star, planet, and galaxy holds a story, inviting us to explore and learn more about the incredible forces that shape the universe. The universe is a wondrous, mysterious place full of remarkable events that unfold over vast stretches of time. One of the most captivating processes is the way galaxies form and evolve, influenced by forces beyond our understanding. It all begins long ago, in the earliest moments after the Big Bang, when the universe was filled with hydrogen and helium. As the universe began to cool, small fluctuations in density allowed gravity to pull the material together, forming the first proto-galaxies. These were the humble beginnings of the magnificent galaxies that would eventually populate the universe. These early galaxies were small, delicate clusters of gas and dark matter. Over time, they merged and combined, growing larger and more complex. The merging of these small galaxies is a key part of what we call the lambda cold dark matter model, which describes how galaxies grow and evolve. As these galaxies came together, their masses increased, and this brought about bursts of new star formation, known as starbursts. During these starbursts, the gas within the galaxies was stirred up and new stars were born, their bright lights piercing the vast darkness of space. When galaxies collide, their shapes can change dramatically. For example, when two spiral galaxies like our Milky Way collide, they may eventually form an elliptical galaxy. The collision of these galaxies disrupts the orderly spiral arms, causing them to dissipate into more rounded, elliptical shapes. Evidence of this can be seen in galaxy clusters, where elliptical galaxies are more common, suggesting that they have undergone multiple mergers over time. The Milky Way, our home galaxy, sits in a relatively quiet region of the universe far from these chaotic mergers. It has retained its spiral shape largely due to fewer collisions. However, as the Milky Way interacts with other galaxies, it is slowly evolving. The stars within spiral galaxies like ours continue to form for billions of years, turning gas into stars, but eventually the gas supply dwindles, and star formation slows down. Over time, the galaxy ages, and its stars grow older, changing from the bright, youthful blue of new stars to the softer red hues of older ones. At the heart of most galaxies, including ours, lies a supermassive black hole. These dark, enigmatic objects have immense gravitational pull, and they play a crucial role in the evolution of galaxies. In fact, the Milky Way's supermassive black hole, known as Sagittarius A, influences the star formation within the galaxy. It is thought that supernovae, the explosive deaths of stars, and the energy from supermassive black holes help regulate how stars are formed and how gas is dispersed across the galaxy. One of the most intriguing mysteries in the universe is dark matter, a substance that makes up about 85% of the mass in the universe, yet cannot be seen. It does not emit, absorb, or reflect light, making it completely invisible to the human eye. Despite its hidden nature, dark matter plays a vital role in the structure of galaxies. It acts like an invisible scaffold, holding galaxies together. Without dark matter, galaxies would not have enough gravitational pull to keep their gas and dust from flying off into space. Dark matter also influences how galaxies interact with one another. When galaxies collide, their dark matter halos pass through each other with little interference. This allows for more frequent galaxy mergers, which can reshape the galaxies and create new structures. The presence of dark matter is what keeps galaxies bound together, even as they spin and twist through space. It also influences the growth of galaxy clusters, which are large groups of galaxies bound together by gravity. Beyond dark matter, there is another mysterious force at work in the universe: dark energy. This substance is thought to be responsible for the accelerated expansion of the universe, pushing galaxies farther apart as time goes on. Dark energy affects the large-scale structure of the universe, helping shape the vast cosmic web of galaxies, stars, and voids. As the universe continues to expand, dark energy makes it harder for galaxies to interact with each other, slowing down the chances of future mergers. As galaxies evolve and merge, new stars are born and older stars die. This endless cycle of birth and death ensures that the universe remains dynamic and ever-changing. Some galaxies, like Andromeda, our nearest neighbour, are on a collision course with the Milky Way. In about 4.5 billion years, the two galaxies will merge into one larger galaxy. Despite the dramatic nature of this collision, the distances between stars are so vast that the stars themselves will not collide. Instead, the gravitational interactions will cause the galaxies to transform, disrupting their spiral shapes and eventually forming an elliptical galaxy. Andromeda is an extraordinary galaxy. Slightly larger than the Milky Way, it contains more than 1 trillion stars compared to our galaxy's 200 to 400 billion stars. The gravitational pull of Andromeda is already having an effect on our own galaxy, drawing it closer. This future merger will change both galaxies, but it will also help scientists understand how galaxies evolve. By studying Andromeda, astronomers can learn about star formation, the dynamics of galaxy interactions, and the life cycles of galaxies. Even though this collision is billions of years away, Andromeda serves as a mirror for the Milky Way, giving us insight into our own future. These two galaxies, forever linked by gravity, tell a story of cosmic transformation, an ongoing dance of creation, destruction, and rebirth. Their eventual merging will be a defining event in the future of our galaxy. The study of galaxy mergers helps us understand the larger picture of the universe. When galaxies collide, their stars, gas, and dust interact in complex ways, triggering bursts of new star formation. These starbursts can be seen as bright flashes of light, as new stars are born in the aftermath of the collision. This process reshapes the galaxies, often turning them from spirals into elliptical shapes. It's in these moments of change that we see the most dramatic transformation of galaxies. At the centre of many galaxies lies a supermassive black hole. When galaxies merge, their supermassive black holes often collide, emitting gravitational waves, ripples in the fabric of space-time. These waves travel across the universe, helping us to understand the immense forces at work in the cosmos. The study of supermassive black holes provides insight into the very nature of gravity, and it is through these cosmic giants that we can begin to grasp the mysteries of the universe. In this ongoing cosmic dance, each galaxy, star, and planet plays a part in a grand story that has been unfolding for billions of years. From the first birth of stars in the early universe to the slow, steady evolution of galaxies, the universe continues to surprise us with its beauty and complexity. Every galaxy, star, and nebula has a story to tell, reminding us that we are all part of something much larger than ourselves. The universe is a constantly evolving tapestry, and we are merely one small thread in the grand, intricate design. Through the study of galaxies, dark matter, dark energy, and supernovae, we are beginning to understand the forces that shape our universe. We have so much more to learn, and every discovery brings us closer to understanding the universe's true nature. Let's drift into a peaceful understanding of the cosmos, where stars, black holes, and distant galaxies move through time in a graceful dance. The universe is a place of wonder and mystery, where galaxies form and evolve over billions of years, slowly growing into majestic shapes and creating new stars as they interact. One of the most awe-inspiring events in the universe is the collision of galaxies. These cosmic encounters play an important role in shaping the stars, gas, and dust within them, making them evolve into new, magnificent forms. Over time, galaxies come together, merging into larger, more complex structures. As they merge, new stars are born in bursts of light, and the resulting galaxies become enriched with heavier elements. These elements, created in the hearts of stars, become the building blocks for future generations of stars. The continuous cycle of cosmic birth and rebirth is a beautiful and mysterious part of the universe's ongoing transformation. At the heart of this process is the gentle pull of gravity, which brings galaxies together, guiding them into new forms. The interplay between gravity and the gas and dust inside the galaxies triggers bursts of star formation. As galaxies collide, their shapes are altered, sometimes forming large, rounded, elliptical galaxies, while others may retain their spiral shapes, still growing and evolving. Now, let's turn our attention to one of the most mysterious and captivating objects in space, the black hole. Imagine a place in the universe where the pull of gravity is so strong that not even light can escape. These cosmic wonders are born from the death of massive stars. When a star much larger than our Sun runs out of fuel, it collapses under its own weight, forming a singularity, a point in space where the density is infinitely large. Surrounding the singularity is a boundary called the event horizon. This is a place beyond which nothing can return. Once something crosses this boundary, it is pulled into the black hole, never to escape. It is as if the fabric of space itself is warped so deeply that it creates a hole in the universe. The forces at play here are beyond comprehension, but they hold an important place in the grand design of the cosmos. While black holes are invisible to our eyes, we can detect their presence by observing the stars and gas around them. If a star orbits a hidden companion, we can infer that it might be a black hole. There is also a glow of radiation emitted by the hot, swirling gas as it is drawn into the black hole, called the accretion disk. Thanks to advancements in technology, scientists can now detect these fascinating objects using gravitational waves, ripples in space-time caused by the collision of black holes. These discoveries have opened up new doors for understanding the nature of the universe. Black holes come in different sizes. Stellar black holes, the most common type, form from massive stars. Supermassive black holes, found at the centers of galaxies, are much larger, with masses millions or even billions of times greater than the Sun. These giants help regulate star formation in their galaxies, guiding the shape and structure of the galaxy itself. Then there are the elusive intermediate black holes, which are still being studied as scientists search for clues to their formation. These black holes provide important insights into the mysteries of the cosmos. As we move through space, we encounter another remarkable object, the neutron star. Imagine an incredibly dense star, so compact that a single teaspoon of its material would weigh as much as all of humanity. This dense remnant is the result of a supernova, a massive star's explosive death. When the star collapses, its core becomes so compact that protons and electrons combine to form neutrons. This process creates a neutron star, one of the densest forms of matter in the universe. Some neutron stars spin incredibly fast, emitting beams of radiation like a lighthouse, creating what are known as pulsars. These stars pulse regularly, with incredible precision, making them one of the most accurate natural clocks in the universe. These regular pulses are so reliable that scientists use them to test the laws of physics, like general relativity. In a more extreme version, we have magnetas, a type of neutron star with magnetic fields thousands of times stronger than those found on Earth. These magnetic fields are so powerful they can distort space itself. Magnetas are fascinating to study because of their extreme conditions, and they help us learn about the forces that shape the universe. Through these fascinating objects, black holes, neutron stars, and pulsars, we gain a deeper understanding of the universe. They are not just enigmatic and mysterious, they are key players in the cosmic drama, showing us the forces at work in the farthest reaches of space. And so, as we drift further into the depths of space, we find that each cosmic phenomenon, whether it's a galaxy colliding, a star dying, or a black hole spinning, is part of an intricate, graceful dance. The universe is always changing, always evolving, in ways both beautiful and mysterious. And while we may never fully understand everything, we can marvel at the wonders it holds, an ever-expanding universe filled with cosmic stories waiting to unfold. Let yourself rest now, knowing that the universe continues its beautiful dance, with stars forming, black holes evolving, and galaxies colliding all in the quiet, infinite space around us. The journey of the cosmos is endless, and in the stillness of the night, it is a reminder of the wonders of the universe, ever present, ever changing, and always there, just beyond the stars. In the vast expanse of space, powerful magnetic fields cause extraordinary events. These fields lead to dramatic bursts of energy, releasing intense X-rays and gamma rays into the universe. These bursts have a profound effect on the stars, especially on their crusts, which are made of ultra-dense neutron-rich matter. This intense energy causes starquakes and more bursts of high-energy radiation, making pulsars and magnetars fascinating objects of study. Pulsars, with their rhythmic pulses of light, help scientists explore the cosmos with precision, acting as cosmic timekeepers. On the other hand, magnetars challenge our understanding of magnetic fields and high-energy astrophysics, with their powerful emissions that reveal the extreme environments of these stars. Both pulsars and magnetars offer us unique windows into the fundamental physics of the universe, pushing the boundaries of what we know about space and matter. These celestial wonders, especially supernova remnants, continue to enrich our understanding of some of the universe's most exotic objects. Among the vast collection of black holes and neutron stars, a few have gained special recognition due to their unique properties, historical importance, and groundbreaking scientific contributions. One of the most famous black holes, Cygnus X1, is located in the constellation Cygnus, about 1,000 light-years away from Earth. Discovered in the early 1970s, Cygnus X1 was one of the first confirmed black hole candidates. This system includes a blue supergiant star and a black hole, whose powerful X-ray emissions are caused by the black hole pulling matter from the supergiant. The discovery of Cygnus X1 played a pivotal role in solidifying the concept of black holes in astrophysics, proving that they exist beyond theoretical predictions. In the world of neutron stars, the Crab pulsar is an iconic object. It sits at the heart of the Crab Nebula, a supernova remnant first recorded by Chinese astronomers in 1054 AD. This pulsar rotates 30 times per second, emitting pulses of radiation across various wavelengths, including radio waves, optical light, X-rays, and gamma rays. Studying the Crab pulsar has provided a wealth of information about pulsar wind nebulae, magnetic fields, and the mechanics of supernova remnants. It remains a cornerstone in multi-wavelength astronomy. Another fascinating black hole is Sagittarius A, located at the centre of our Milky Way galaxy. Though invisible to optical telescopes, its presence is inferred through the rapid orbits of nearby stars. These stars orbit an unseen, massive object whose gravitational pull is immense. Through radio and infrared observations, astronomers have confirmed that Sagittarius A has a mass approximately 4 million times that of our Sun. This discovery has provided invaluable insights into the nature of supermassive black holes and their role in galaxy formation and evolution. Neutron stars have long fascinated scientists, especially the pulsar PSR B1919+21, the first pulsar ever discovered. In 1967, Jocelyn Bell and Anthony Hewish detected its periodic radio pulses, initially leading to speculation about extraterrestrial intelligence. However, it was later identified as a rapidly rotating neutron star emitting beams of radio waves. This discovery opened a new era in observational astrophysics, revealing new ways to study the extreme physics governing neutron stars. These famous black holes and neutron stars are not just objects of curiosity, they are monumental in advancing our understanding of stellar evolution, gravitational theory, and extreme states of matter. By continuing to explore these objects, we push the boundaries of what we know about the universe. The Big Bang Theory, which explains the origin of the universe, serves as the prevailing cosmological model. According to this theory, the universe began about 13.8 billion years ago from an extremely hot and dense state and has been expanding ever since. However, the Big Bang should not be thought of as an explosion in the traditional sense. Instead, it marks the beginning of space-time and the creation of all the matter and energy in the universe. The Big Bang Theory is supported by multiple lines of evidence. One of the most compelling pieces comes from the observation of cosmic microwave background radiation, CMB. First detected by Arno Penzias and Robert Wilson in 1965, the CMB is a faint glow that fills the universe. This radiation is considered the afterglow of the Big Bang and provides a snapshot of the infant universe when it was just 380,000 years old. The radiation is remarkably uniform, with tiny fluctuations that correspond to the seeds of all current cosmic structures, galaxies, stars, and planets. Another line of evidence is the redshift of galaxies, first described by Edwin Hubble. Hubble observed that galaxies appear to be moving away from us, with their light shifted toward the red end of the spectrum. This indicates that space itself is expanding, which aligns with Albert Einstein's theory of general relativity. By tracing this expansion backward, we can see that the universe was once much more condensed. Additionally, the abundance of light elements such as hydrogen, helium, and traces of lithium, as predicted by Big Bang nucleosynthesis, further supports this theory. These elements were formed during the first few minutes of the universe, when temperatures and pressures were so high that nuclear reactions could occur, creating these primordial elements in the quantities we observe today. The Big Bang theory offers a comprehensive framework for understanding the universe's origin and evolution. It not only explains current observations, but also continues to guide new discoveries, helping us enhance our understanding of the cosmos as it evolves over billions of years. Determining the age and size of the universe involves a combination of observational astronomy, theoretical physics, and advanced mathematical modeling. One of the key methods is studying the cosmic microwave background radiation, CMB, which is the oldest light in the universe. By analyzing tiny fluctuations in the CMB, scientists can infer crucial cosmological parameters, such as the rate of expansion of the universe, known as the Hubble constant. Observatories like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have provided precise measurements of these fluctuations, leading to the most accurate estimates of the universe's age. Current calculations suggest that the universe is approximately 13.8 billion years old. Another approach involves studying the oldest known star clusters, such as globular clusters. These dense groups of ancient stars provide a lower bound on the age of the universe. By determining the age of the oldest stars within these clusters, astronomers can validate and refine the age derived from the CMB data. Measuring the size of the universe, particularly the observable universe, is closely tied to understanding its expansion. Hubble's observation that galaxies are receding from us, with more distant galaxies moving faster, led to the estimation of cosmic scale. The Hubble constant, which quantifies this expansion rate, is critical for calculating distances. Modern measurements using Type 2a supernovae as standard candles and baryon acoustic oscillations, BAO, help refine the value of the Hubble constant and improve our understanding of cosmological distances. Since light travels at a finite speed, looking into space is also like looking back in time. The observable universe forms a sphere around us, with a radius of about 93 billion light-years. This is far larger than the age of the universe multiplied by the speed of light due to the continuous expansion of space. By examining the CMB, star clusters, supernovae, and cosmic expansion, scientists piece together a picture of the universe's vast age and size. Their discoveries provide profound insights into the observable boundaries of the cosmos and its dramatic history. The cosmic microwave background, CMB radiation, is a pervasive afterglow of the Big Bang. It fills the universe as faint microwave radiation and offers a glimpse into the early universe, when light was first able to travel freely. This discovery, made in 1965, has helped scientists understand the universe's timeline, providing a snapshot of its birth and giving us a deeper understanding of how the universe evolved to become what we see today. The cosmic microwave background, CMB, is like a snapshot of the universe when it was very young. It's an incredibly important discovery in understanding the cosmos. The CMB is a faint glow, which fills the universe and represents the leftover energy from the Big Bang. This energy gives us a look back at the universe when it was just a few 100,000 years old. The uniformity of the CMB is one of the strongest pieces of evidence for the Big Bang theory. The tiny variations, about 1 part in 100,000, are tiny but important. They show us the early stages of the universe and how small differences in density grew over billions of years into the stars, planets, and galaxies we see today. Thanks to space missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, scientists have gathered detailed information from the CMB. These measurements help us understand things like how fast the universe is expanding, how much dark matter and dark energy there is, and how much regular matter is out there. The study of the CMB has also helped scientists determine the universe's age, about 13.8 billion years. The CMB has also given us clues about a fascinating process known as cosmic inflation. After the Big Bang, the universe expanded rapidly. This sudden expansion, which happened in the first fractions of a second, is still visible in the temperature and polarization patterns found in the CMB. These patterns give scientists insights into the very early universe and open new paths to study physics at energies far higher than anything we can test on Earth. Cosmic background radiation is like a time capsule from the universe's birth. helping us piece together its early history. It shows us how the universe evolved from that tiny hot beginning to the vast structured form it has today. This radiation continues to be a vital source of information, helping guide our understanding of the cosmos. To understand how the universe expands, scientists study distant galaxies and the light they send out. One key method to measure this expansion involves looking at something called redshift. This happens when galaxies move away from us, stretching the light they emit toward the red end of the spectrum. By studying how much the light shifts, we can understand how fast these galaxies are moving and, in turn, how fast the universe is expanding. This method relies on the Hubble constant, a number that helps us understand the expansion rate. Edwin Hubble first noticed that galaxies are moving away from us, and the farther away they are, the faster they move. This relationship helps us calculate how quickly space itself is stretching. To measure the Hubble constant, astronomers use standard candles like type Ia supernovae, which are exploding stars with a known brightness. By comparing their known brightness to how bright we observe them to be, scientists can calculate how far away they are and thus help refine our understanding of the universe's expansion. The cosmic background radiation, which represents the leftover energy from the Big Bang, also helps in understanding expansion. The temperature variations in the CMB provide a glimpse into the early conditions of the universe. By analysing these variations, we can get a better sense of how the universe's geometry and expansion rate have changed over time. Additionally, scientists use a method known as baryon acoustic oscillations, BAO, to measure cosmic distances. These fluctuations were caused by sound waves in the early universe, and their effects can be seen in how galaxies are spread across the universe. By measuring the scale of these fluctuations, astronomers can refine their understanding of the universe's expansion rate. Studying the universe's expansion involves a combination of observing distant galaxies, supernovae, the cosmic background radiation, and large-scale cosmic structures. Together, these methods give scientists a fuller picture of how space has stretched and grown since the Big Bang. The expansion of the universe continues to guide our understanding of the ever-changing cosmos. As we look forward, one of the most profound questions in cosmology is the ultimate fate of the universe. There are several theories that describe how the universe may end, and each theory depends on the properties of dark energy, dark matter, and the overall expansion of the universe. One theory is called the Big Freeze, or heat death. This scenario suggests that the universe's expansion will continue indefinitely, driven by dark energy. Galaxies will drift farther apart and stars will eventually run out of fuel, leaving a universe full of cold remnants like white dwarfs, neutron stars, and black holes. Over an incredibly long time, even black holes may slowly evaporate, and the universe will become a cold, empty space. Another theory is the Big Crunch. In this model, the universe's expansion could stop and reverse, with gravity overcoming dark energy. Galaxies would come together, increasing the density and temperature of the universe, potentially collapsing into a singular point, like the Big Bang. This theory suggests the universe could have a cyclical pattern of expansion and contraction. A related theory is the Big Bounce. In this model, after contracting into an extremely dense state, quantum effects could cause the universe to rebound and expand again, beginning another cycle of creation. This theory attempts to merge quantum mechanics with general relativity to explain the behavior of the universe in extreme conditions. There is also the Big Rip scenario. In this model, if dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms. Space itself would be torn apart, leading to a dramatic end where everything in the universe is ripped apart. Finally, there's the heat death scenario, where the universe reaches a state of thermodynamic equilibrium. In this state, all energy is evenly spread out, and there are no differences in temperature or energy to drive any process. The universe would become a uniform, featureless expanse, and time would essentially stop. These theories are still being refined as we continue to learn more about dark matter, dark energy, and the fundamental forces at work in the cosmos. Observations from new technologies, like the James Webb Space Telescope and gravitational wave detectors, will provide even more insights into the universe's fate. The study of dark matter and dark energy is one of the most exciting areas of modern astronomy. Although we can't directly observe these mysterious components because they don't interact with light in the same way visible matter does, scientists have come up with clever ways to study them. We know dark matter exists because it affects the way galaxies rotate and influences the large-scale structure of the universe. When scientists observe the speeds at which stars rotate within galaxies, they notice that the stars on the outer edges move faster than expected, based on the visible matter alone. This discrepancy suggests there's an unseen mass, dark matter, affecting the galaxy's rotation. These discoveries continue to shape our understanding of the universe and guide the exploration of its mysteries. Dark matter and dark energy are two mysterious forces that shape the vast universe around us. While they remain unseen, they influence nearly every aspect of the cosmos, acting as invisible guides in the background. Dark matter, which makes up about 85% of the universe's total mass, doesn't interact with light, so we can't see it directly. Instead, scientists look at how it affects the things we can see, like the movement of galaxies. For example, the light from distant galaxies doesn't behave the way we would expect from visible matter alone. It bends in ways that suggest something unseen is there, pulling the stars and gas with its invisible gravity. To detect dark matter, scientists are using clever methods like special underground detectors, shielded from the radiation of cosmic rays, and experiments at high-energy particle colliders, like the Large Hadron Collider. These methods allow researchers to look for any rare interactions between dark matter and regular matter, in hopes of revealing more about its nature. Meanwhile, dark energy, which makes up around 70% of the universe's total energy, is thought to be driving the accelerated expansion of space. The idea came to light when astronomers noticed that distant galaxies appeared dimmer than they should be, suggesting that the universe's expansion is speeding up. Even though we don't fully understand dark energy, we know it's a driving force in the universe's growth. Scientists study dark energy by observing galaxies and the structures of space itself. Through surveys like the Sloan Digital Sky Survey and the Dark Energy Survey, astronomers map out galaxies and cosmic voids to track how they change over time. They also examine the cosmic microwave background, CMB, the faint afterglow from the Big Bang, to learn about the early universe. Instruments like the Planck satellite give us detailed measurements, helping scientists understand how the universe expanded, how galaxies formed, and the role dark energy plays in this process. One day, advanced telescopes like the James Webb Space Telescope and future space missions will provide even more data, helping us get closer to understanding both dark matter and dark energy. These forces, while elusive, are the key to unlocking many of the universe's greatest mysteries. Now, let's shift our focus to exoplanets, planets that orbit stars outside our solar system. Since 1992, when the first exoplanets were discovered, our knowledge of these distant worlds has grown tremendously. Today, thousands of exoplanets have been catalogued, offering us a glimpse into the diversity of planetary systems out there. One of the most common ways to find exoplanets is by using the transit method. This technique watches the light from a star to see if it dims slightly at regular intervals. When a planet passes between us and the star, it blocks some of the light, and by measuring how much and how often this happens, astronomers can learn about the planet's solar orbit and even its atmosphere. NASA's Kepler Space Telescope helped discover over 2,000 confirmed exoplanets using this method. Another effective method is radial velocity, also called the Doppler method. This looks at the slight wobble of a star as a planet orbits it. The planet's gravity tugs on the star, causing it to move slightly. When the star moves toward us, its light shifts to a slightly blue hue. When it moves away, it shifts to red. By studying these shifts, scientists can calculate the planet's mass and orbit. Telescopes like the HARP spectrograph in Chile have been key to this discovery process. Gravitational microlensing is another exciting method for discovering planets, especially those that are far away. It happens when a massive object like a star bends the light from a more distant star. If a planet orbits this star, It can cause a brief brightening in the light of the distant star, giving scientists a clue that a planet is there. Some other techniques, like direct imaging, help astronomers capture actual pictures of exoplanets. By blocking out the bright light of the star with special tools like a coronagraph, telescopes can take pictures of planets and even study their atmospheres. The James Webb Space Telescope will help us learn even more about exoplanet atmospheres, revealing what makes them unique. Finally, astrometry measures the small wobbles in a star's position caused by the pull of an orbiting planet. Although this method requires very precise measurements, it's great for finding planets with longer orbits. Each of these methods brings us closer to understanding exoplanets and their potential for habitability. By studying them, we not only learn more about how planets form, but we also get closer to answering the big question: is there life beyond our solar system? The study of exoplanets, or planets that orbit stars outside our solar system, opens a window into a vast and mysterious world. Each exoplanet is different, with unique sizes, compositions, and orbits. It's a fascinating journey to understand the diversity of these distant worlds, some of which could possibly harbour life. With tools like NASA's TESS Transiting Exoplanet Survey satellite, the James Webb Space Telescope, and ESA's Plato mission, astronomers have been able to study exoplanets in ways never imagined before. These advancements allow scientists to uncover more details about these faraway planets, revealing their potential to support life. One of the key factors in determining whether an exoplanet can support life is its ability to keep liquid water, an essential ingredient for life as we know it. The planet's location within its star's habitable zone, often called the Goldilocks zone, is crucial. This is the sweet spot where the temperature is just right, not too hot, not too cold, for water to exist in liquid form on the planet's surface. The habitable zone around a star depends on the type of star it is. For example, around a Sun-like star, the habitable zone stretches from 0.95 to 1.37 astronomical units, AU, with 1 AU being the distance from Earth to the Sun. For cooler stars like M dwarfs, the habitable zone would be much closer in. Discovering an exoplanet within this zone is an exciting first step toward understanding whether it might be habitable. Size and composition are also important. Ideally, a habitable exoplanet should be Earth-sized, meaning it has a similar mass and radius. This suggests it has a rocky surface, not a gas-filled atmosphere like Jupiter or Neptune. If the planet is too large, it may develop a thick hydrogen and helium atmosphere, making it more like Neptune. On the other hand, planets that are much smaller than Earth might not be able to hold on to a thick atmosphere, which is crucial for protecting life and maintaining liquid water. The planet's atmosphere plays a huge role in its ability to support life. A planet's atmosphere helps to regulate the temperature, keeping it warm enough for liquid water without getting too hot. It also provides the gases necessary for biological processes, like oxygen and carbon dioxide. The right balance is key. If the atmosphere is too thick, it could create a runaway greenhouse effect like what we see on Venus. But if it's just right, it could support life. Observatories like the James Webb Space Telescope are helping us study the atmospheres of these far-off worlds. By observing the light that passes through the atmosphere, scientists can look for signs that a planet might be able to sustain life. They can detect molecules like water vapor, carbon dioxide and methane, which are promising signs of habitability. Another important factor is the stability and activity of the host star. Stars that are too active with frequent solar flares could strip away a planet's atmosphere, making it harder for life to survive. Stars like our Sun, which have stable light and long lifespans, are more likely to support life on their planets. Interestingly, M dwarfs, which are dimmer and cooler than our Sun, have very long lifespans. However, their frequent flares can pose risks to habitability. Other factors like the planet's tilt and its orbit around its star also play a role in its ability to support life. The tilt affects seasons, while the orbit affects climate stability. A planet with a magnetic field can also help protect its atmosphere from harmful solar winds and cosmic radiation. Recent discoveries have revealed a few intriguing candidates for potentially habitable exoplanets. One of them is Proxima Centauri b, located in the habitable zone of the closest star to the Sun, just over 4 light-years away. This planet's proximity and location make it a tantalizing target for further study. In the TRAPPIST-1 system, 7 Earth-sized planets orbit a cool dwarf star just 39 light-years away. 3 of these planets are located in the star's habitable zone. Studies of these planets suggest they might also have the right conditions to support life. These planets are a fascinating opportunity to study exoplanetary atmospheres and explore life beyond Earth. The search for exoplanets is one of the most exciting areas of modern astronomy. As our technology improves, telescopes like the James Webb Space Telescope, along with other new missions, will provide even more detailed information. These discoveries will help us understand not only the conditions necessary for life, but also whether we might find life elsewhere in the universe. In our quest to understand the possibility of life beyond Earth, the Drake equation offers an intriguing framework. This equation was developed by astrophysicist Frank Drake in 1961 to estimate the number of communicative extraterrestrial civilizations in our galaxy. The equation breaks down the question into manageable factors, such as the rate of star formation, the number of stars with planets, and the number of planets where life might develop. Despite the uncertainties in some of these factors, the Drake equation has helped scientists refine their search for extraterrestrial intelligence. By incorporating new discoveries, such as the detection of exoplanets and the study of their atmospheres, we can continue to improve our estimates. This ongoing work helps address one of the most profound questions: are we alone in the universe? The quest to find life beyond our solar system is not just about looking for planets like Earth, but also understanding how life could exist in environments far different from our own. The more we learn about exoplanets, the more we expand our understanding of the universe and our place in it. Imagine the awe of watching 2 astronauts, Neil Armstrong and Buzz Aldrin, step onto the surface of the Moon for the very first time. It was an incredible achievement that showed the amazing power of human ingenuity and determination. When Armstrong spoke those famous words, "That's one small step for man, one giant leap for mankind," he perfectly captured the importance of this historic moment. The Apollo missions were more than just a visit to the Moon. They brought back over 840 pounds of rocks, soil and core samples, which completely changed our understanding of the Moon. These samples helped scientists learn more about the Moon's structure and history. But the Apollo missions weren't just about collecting data. They were about pushing the boundaries of what science and technology could achieve. The Saturn V rocket, the most powerful rocket ever built, carried astronauts past Earth's atmosphere, showing the world the incredible power of engineering and science. The experiments left behind on the Moon, like seismometers and retroreflectors, gave us valuable insights into the Moon's inner structure and how it interacts with Earth. Apollo 12 through Apollo 17 extended our exploration with more missions, using the lunar roving vehicle to travel further across the surface, collecting even more data. These missions laid the foundation for modern space exploration and inspired generations of scientists to dream big. The International Space Station, ISS, stands as another incredible example of global collaboration. Orbiting Earth at about 250 miles above the surface, the ISS has been a vital platform for scientific experiments that would be impossible on Earth. By studying the effects of living in microgravity, scientists have learned how space travel impacts the human body, including changes to muscles and bones. This research will help future astronauts who may journey to Mars and beyond. The ISS is not just a place for studying human health, it's a laboratory for physics, helping scientists understand things like fluid dynamics and combustion in space. The station also plays an important role in studying Earth's atmosphere, oceans and land surfaces, helping us track climate change and natural disasters. The cooperation between countries working on the ISS also demonstrates how space exploration can bring nations together, as scientists from around the world work to unlock the secrets of the universe. On Mars, the Curiosity and Perseverance rovers are on a mission to uncover the secrets of the Red Planet. These robotic explorers have been analysing rock and soil samples, searching for signs of past life and studying Mars' climate and geology. Curiosity, which landed on Mars in 2012, found evidence of ancient riverbeds and lakes, suggesting that Mars may have once supported life. Perseverance, which arrived in 2021, builds on these discoveries and is working to collect soil and rock samples that could contain traces of ancient life. It's also using groundbreaking technology to study the planet's surface and climate, preparing for the future of human exploration. In addition to its scientific achievements, Perseverance carries a special addition: Ingenuity, a small helicopter that has proven powered flight is possible on another planet. This breakthrough opens the door for new types of exploration in space. Together, these rovers are laying the groundwork for human missions to Mars, and every new discovery helps us understand more about the planet's history and its potential for supporting life. The Voyager and New Horizons missions also represent remarkable achievements. Launched in the late 1970s, the twin Voyager spacecraft embarked on an incredible journey to study the outer planets of our solar system. Voyager 1 and Voyager 2 sent back incredible images of Jupiter, Saturn, Uranus, and Neptune, giving us a deeper understanding of these far-off worlds. They revealed the beauty of Jupiter's rings, the complex atmospheres of Saturn and Neptune, and even the active volcanoes on one of Jupiter's moons, Io. After their successful tour of the outer planets, both Voyager spacecraft entered interstellar space, becoming the first human-made objects to leave the influence of our Sun. Their instruments continue to send back valuable data about the space beyond our solar system, helping us better understand our place in the galaxy. New Horizons, launched in 2006, had a unique mission to study Pluto and the Kuiper Belt. After nearly a decade of travel, it passed Pluto in 2015, revealing stunning details about this distant dwarf planet. The mission showed Pluto's mountains and vast nitrogen ice plains, completely changing our view of this distant world. But New Horizons didn't stop there. After its Pluto flyby, it was directed to another target in the Kuiper Belt, an object named Arakoth. This encounter provided a glimpse into the early days of our solar system, showing a pristine world with a surprisingly smooth surface. These missions are a testament to humanity's endless curiosity and desire to explore the unknown. They have given us a wealth of knowledge and continue to inspire future generations to dream big and aim high. Looking ahead, the next steps for space exploration are equally ambitious. NASA's Artemis program plans to return humans to the Moon, including the first woman and the next man, by the mid-2020s. The goal is to create a sustainable human presence on the Moon by the end of the decade. This includes building the Lunar Gateway, a space station that will orbit the Moon and serve as a hub for future missions. Exploring the Moon's surface will allow scientists to study its resources, like water ice, which could now be used for life support and fuel, making it easier for humans to live on the Moon. Studying the Moon's geology will also help us understand the early solar system, providing clues about how Earth and other planets formed. But the most exciting part of future space exploration is Mars. NASA, private companies like SpaceX, and other international partners are working towards sending humans to Mars. These missions will build on the foundations laid by the robotic rovers, Curiosity and Perseverance, and focus on creating habitats that can survive Martian conditions, extracting water and oxygen from the planet, and developing sustainable energy solutions. The goal is to search for signs of past life, study Mars' climate and geology, and understand its history. This will involve drilling into the Martian surface and even returning samples to Earth for detailed analysis. Every step we take in space exploration brings us closer to understanding the mysteries of the universe, and each mission helps us prepare for the exciting future of exploring worlds beyond our own. As we look toward the stars, we know that with each new discovery, we are unlocking the secrets of the cosmos and taking another step toward becoming a part of it. These incredible missions don't just answer our deepest questions about Mars, they also help prepare us for the future, a future where humanity could live on another planet. With each new discovery, we take a step closer to becoming an interplanetary civilization, exploring the unknown with curiosity and determination. Space telescopes like the Hubble Space Telescope and the James Webb Space Telescope have opened our eyes to the wonders of the universe. Their incredible views have allowed us to see distant galaxies, nebulae and stars in ways that were once unimaginable. Since Hubble was launched in 1990, it has captured breathtaking images that reveal the beauty and mystery of the cosmos. These observations have taught us so much, like the discovery that the universe is expanding faster than we thought. This was first noticed by studying distant supernovae, which led scientists to think that something mysterious, something called dark energy, is causing this expansion. Hubble has also helped us learn about the life cycles of stars and how galaxies are formed and change over time. By capturing clear images of the early universe, we can see the birth of the first galaxies and stars. It helps scientists study the universe from all angles, with the ability to observe ultraviolet, visible, and near-infrared light. This versatility makes Hubble a precious tool for astronomy. Then there's the James Webb Space Telescope, which was launched in December 21. Webb's main power lies in its ability to observe the universe in infrared light, allowing it to peer through clouds of cosmic dust that block our view. Webb's primary mission is to look back to the very first moments after the Big Bang, capturing the earliest light-emitting objects and studying how the first galaxies formed. It will also examine the atmospheres of exoplanets, searching for signs that these distant worlds could support life. Together, Hubble and Webb make an extraordinary team, each with its own unique capabilities. They complement one another and allow us to learn more about the universe than we ever thought possible. Their combined efforts are expanding our knowledge of space, bringing us closer to the possibility of discovering new worlds and understanding the vastness of the cosmos. Dark matter, though invisible to our eyes, is one of the most important components of the universe. It doesn't emit light, absorb light, or reflect light, which makes it a mystery that we can only detect through its effects on the things around it. Scientists believe dark matter makes up about 27% of the universe, while the ordinary matter that we can see, like stars, planets, and galaxies, makes up only about 5%. The remaining 68% of the universe is thought to be made up of dark energy, a mysterious force that is causing the universe to expand faster and faster. The search for dark matter has been going on for many years, ever since the 1930s, when astronomer Fritz Zwicky first noticed that galaxies in the Coma cluster were moving much faster than expected. Later, in the 1970s, Vera Rubin's work on galaxies helped confirm that the outer parts of galaxies were spinning too fast to be explained by just the visible stars and gas. This led scientists to realize that there must be something else, something invisible, pulling on the galaxies, and they named it dark matter. Dark matter is crucial because it acts like the scaffolding for galaxies and clusters of galaxies. Without dark matter, these cosmic structures wouldn't have formed the way we see them today. It also helps us understand gravitational lensing, where the light from distant stars is bent around massive objects like galaxy clusters. This bending effect allows us to map the distribution of dark matter across the universe. Although we haven't been able to directly detect dark matter yet, scientists are actively searching for it. There are several theories about what dark matter might be, like weakly interacting massive particles, WIMPs, or axions, and understanding it could lead to new breakthroughs in physics. Alongside dark matter, there's dark energy, a force that's making the universe expand faster. It was first noticed in the 90s when scientists observed that distant supernovae were dimmer than expected, suggesting that the universe's expansion rate was speeding up. Dark energy makes up about 68% of the universe's total energy content, but like dark matter, it's something we can't see directly. Instead, scientists study its effects on galaxies and the expansion of space. To learn more about dark energy, scientists use a few different methods. One involves studying Type Ia supernovae, which act as standard candles in space. These supernovae are always the same brightness, so scientists can use them to measure distances in space. By comparing the observed brightness of a supernova to its redshift, scientists can figure out how much the universe has expanded since the light left the supernova. Another method is looking at the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB tells us a lot about the early universe, its expansion, and the role dark energy has played in shaping it. Large-scale surveys of galaxies and their distribution also help scientists understand how dark energy affects the universe over time. Dark energy is still a mystery, but as new observations and experiments continue, we are slowly piecing together the puzzle. The upcoming missions, like the Euclid Telescope and the Wide Field Infrared Survey Telescope, WF-FIRST, will help gather even more detailed data, bringing us closer to understanding this profound force that shapes our universe. Gravitational waves are another exciting discovery. These ripples in space-time were first predicted by Albert Einstein over 100 years ago, and in 2015 they were finally detected. Gravitational waves are caused by massive objects, like black holes or neutron stars, that disturb the fabric of space-time. These waves travel at the speed of light, carrying energy away from their source. The detection of these waves opened up a whole new way of observing the universe. Instruments like LIGO, Laser Interferometer Gravitational Wave Observatory, were created to detect these subtle waves. LIGO has two facilities, one in Livingston, Louisiana, and one in Hanford, Washington, and they work together to measure the tiny distortions in space-time caused by gravitational waves. Gravitational waves give us a new way to observe the universe beyond the usual light-based observations. They allow scientists to study black holes, neutron stars, and other cosmic phenomena that were previously invisible to us. Imagine a vast, peaceful universe filled with mysteries we are just beginning to understand. Some of the most exciting discoveries in space come from things we can't see directly, but we feel their presence through tiny changes in the world around us. One such discovery is the fascinating idea of gravitational waves. These waves are ripples in space-time, like gentle waves spreading out on a quiet pond, caused by big, powerful events like two black holes merging far, far away. When a gravitational wave passes through Earth, it stretches and squeezes space ever so slightly, making tiny changes that can be detected by special instruments. The very first gravitational wave detection, called GW-0914, came from the merger of two black holes 1.3 billion light-years away. Imagine two black holes, each as heavy as many suns, spiraling closer together before merging into a new, larger black hole. This event released an incredible burst of energy, creating the gravitational waves we can now measure, giving us a new way to learn about the universe and explore things we couldn't see before. Since then, there have been more discoveries, including the detection of neutron star mergers, where two stars crashed together and created both gravitational waves and light. It was a special moment for science because it marked the beginning of what we call multi-messenger astronomy, where we look at the universe through both light and gravitational waves to see a bigger picture. With the addition of more detectors like Virgo in Italy and Kagra in Japan, we are learning even more about the forces that shape our universe. Another mystery comes from fast radio bursts, or FIs, which are quick bursts of radio waves that can release as much energy in just a few milliseconds as the sun does in an entire day. These bursts appear so suddenly that scientists are still working to understand where they come from. Some of these bursts are one-time events, while others repeat, and we're just beginning to figure out why. One of the repeating bursts was traced back to a star-forming region in a distant galaxy, helping us understand a little more, but many questions still remain. One signal, known as the WOW signal, was detected in 1977 by a radio telescope, and it left scientists wondering if it could be a message from an extraterrestrial civilization. Though no similar signals have been found, this discovery continues to spark curiosity and wonder about the possibility of life beyond Earth. These mysterious signals, such as FARBs and the WOW signal, are not only puzzles but also inspire new technologies and methods to help us listen to the universe. With new tools like the CHIME and ASCAP telescopes, scientists are getting better at finding and studying these elusive bursts, increasing our understanding of the cosmos. One day, these signals might reveal more about the fundamental forces that shape our universe. But there is another big question that scientists continue to explore. Are we the only ones in the universe, or are there other worlds, other civilizations? The idea of parallel universes, or the multiverse, suggests that our universe might be just one of many, each existing separately and possibly governed by different laws of physics. One idea, called the many worlds interpretation of quantum mechanics, suggests that every possible outcome of a quantum event happens in a different universe. If a particle has two possible states, our universe would split into two, each one realizing a different outcome. This idea leads to the possibility of an infinite number of parallel universes, each one experiencing a different version of reality. Another idea, from the theory of eternal inflation, suggests that our universe might be just one bubble in an ever-expanding multiverse. Some parts of space may have stopped inflating, creating distinct universes like ours, while other parts continue to expand, forming new universes. This theory opens up the possibility that there are many different universes, each with its own unique set of rules. String theory, a theory in physics, suggests that the different universes could be made from different strings, tiny vibrating particles that make up everything in the universe. Each universe could be a different version of the laws of physics, giving us an endless variety of possible worlds. And then there's the idea of brain worlds, where our universe is just one of many floating in higher dimensional space. These different universes might sometimes interact or even collide, possibly explaining cosmic events like the Big Bang. These theories of parallel universes and the multiverse offer a wonderful glimpse into the unknown. They suggest that the universe we know might be just one part of a much bigger and more complex reality. While we don't have proof of parallel universes yet, scientists are working hard to uncover the secrets of these mysteries. And who knows? Maybe one day we'll find answers that change the way we understand existence itself. Another fascinating part of space science comes from the study of quasars and blazars, some of the brightest and most energetic objects in the universe. Quasars are incredibly luminous, powered by supermassive black holes at the centers of galaxies. As matter falls into these black holes, it forms a glowing accretion disk, sending out intense radiation across the entire electromagnetic spectrum, from visible light to X-rays and even gamma rays. These bright objects can be seen from billions of light years away, acting as cosmic beacons that help us study the distant universe. Blazars are a special type of quasar, with their powerful jets of energy pointed directly toward Earth. These jets shine even brighter, making blazars incredibly bright and dynamic. The study of quasars and blazars gives us insight into the behavior of matter under extreme conditions near the event horizon of a black hole, and helps us understand the fundamental forces at play in the universe. As we continue to explore the cosmos, we learn more about the incredible processes that shape our universe. These discoveries, whether it's the mysterious signals from distant stars or the possibility of parallel universes, inspire us to keep looking deeper into the unknown. Each new step in our exploration brings us closer to understanding the vast and beautiful universe we call home. Blazars are fascinating objects that astronomers study to understand how jets are formed, how particles move, and how these jets interact with space. To learn more about these cosmic wonders, scientists use a variety of tools that capture energy across the whole electromagnetic spectrum. Radio telescopes like the ones at the Very Large Array and the Atacama Large Millimeter Array help us understand the radio waves emitted by blazars and quasar jets. These observations give us a closer look at how the jets move and what they're made of. On top of that, telescopes like the Hubble Space Telescope observe the light around the accretion disk, helping us learn more about these distant objects. X-ray telescopes like Chandra and gamma-ray telescopes also help by studying high-energy emissions, offering clues about how particles accelerate and release energy in jets. By studying these emissions, scientists also use spectroscopy to learn about the distance of these objects, their chemical makeup, and how fast they are moving. All of this helps us understand the immense black holes at the center of these objects, as well as the dynamics of the jets. Theoretical models, which are like predictions based on what we observe, help guide scientists in understanding the behaviors of these cosmic objects. Together, the observations and theories shed light on how galaxies form, how black holes grow, and how the universe itself is evolving. Astrobiology, the study of life beyond Earth, is a beautiful field that blends biology, chemistry, physics, and astronomy. Scientists in this field are working hard to answer one of the most exciting questions: are we alone in the universe? Astrobiologists study life here on Earth in extreme places, like hot springs or deep under the ocean, to understand how life could exist in such tough conditions. By studying these extremophiles, organisms that thrive in the harshest environments, scientists get important clues on where to look for life elsewhere in space. Some of these extreme organisms survive intense heat, high radiation, or even under ice, which gives us hope that life could exist in places like Mars or the moons of Jupiter and Saturn, such as Europa and Enceladus. These moons have vast oceans beneath their icy surfaces, and scientists believe that just like Earth's deep-sea vents, these environments could support life. For example, Mars has long been a target in the search for life. It's believed that Mars once had liquid water, which is essential for life. Recent discoveries, such as methane plumes and dark streaks on the surface, suggest that liquid water could still flow there today. The Curiosity rover has found complex molecules in the soil, which strengthens the idea that life could have existed there in the past. Europa and Enceladus, moons of Jupiter and Saturn, are also exciting. Europa's thick ice crust covers an ocean of water heated by Jupiter's gravitational pull. Similarly, Enceladus has geysers that eject water and organic molecules into space, which means these moons could harbour microbial life deep beneath the surface. To find out more, researchers are sending robotic explorers like the Perseverance rover to Mars. This rover is studying an ancient riverbed to learn more about Mars's past and look for signs of ancient life. By exploring these environments, we're uncovering the secrets of how planets can support life, and perhaps even discovering new life in the process. The search for life doesn't stop with our own solar system. Telescopes like the James Webb Space Telescope are helping scientists study distant planets that orbit other stars. We're learning how to detect signs of life on these exoplanets by looking at their atmospheres, searching for the same conditions that support life on Earth. Finding life beyond Earth would change everything we know about biology, about life's adaptability, and about our place in the universe. It would show that life isn't limited to Earth's unique conditions. This discovery could spark deep philosophical questions about what it means to be human, about our role in the cosmos, and about our responsibility to protect Earth. It would also lead to breakthroughs in science and technology, just as the space race did decades ago, improving life on Earth with new innovations. As we continue our search for life, we're making technological advances that will help us live in space. We're learning how to create habitats on Mars, extract resources from other planets, and even find ways to survive on distant worlds. Every new discovery brings us closer to understanding how life can thrive beyond Earth, and how we might one day join the stars. Finding life beyond Earth is not only about understanding biology, but also reshaping our culture and technology. Scientists are using powerful space telescopes to look for signs of life on other planets. One such telescope, the James Webb Space Telescope, helps detect chemicals in the atmospheres of distant planets by studying the light that passes through them. By examining this light, scientists can find molecules like oxygen, methane, and water, which could be signs of life. Scientists also use advanced techniques to block out the bright light from a planet's star, allowing them to study the faint light from the planet. This method can help them find surface features and atmospheric details that may reveal life signs like chlorophyll, the substance plants use to make food. The extremely large telescope being built in Chile will help study exoplanets and their atmospheres, searching for unusual gases or colours that could suggest biological activity. Human colonization of Mars is one of the most exciting challenges for space agencies and private companies. Mars is the most viable planet for colonization because it is relatively close to Earth and has the potential for using its resources. NASA and SpaceX are developing technologies to make Mars habitable. One of the key ideas is using resources from Mars itself, like its atmosphere and soil, to create water, oxygen, and building materials. However, there are many challenges to making Mars livable. One of the main concerns is protecting astronauts from radiation, as Mars doesn't have a strong magnetic field or thick atmosphere to shield them. Another major concern is keeping astronauts healthy during long missions in space. Research is being done on exercise equipment to help prevent muscle loss and bone density reduction. There are also efforts to protect astronauts from the harmful effects of space radiation using innovative materials and shielding. Psychological health is also critical for long-duration space missions. Space agencies are developing better spacecraft designs to make astronauts more comfortable, and using virtual reality to simulate Earth-like environments. They're also working on systems that allow astronauts to operate independently when communication with Earth is delayed. Private companies like SpaceX are playing a significant role in space exploration. They are making space travel more affordable and accessible. SpaceX has developed reusable rockets that can reduce the cost of missions, and their spacecraft are taking supplies and astronauts to the International Space Station. SpaceX is also working on Starship, a spacecraft designed to carry humans to Mars. In the near future, space tourism is expected to grow rapidly. Companies like SpaceX, Blue Origin, and Virgin Galactic are offering suborbital flights that allow tourists to experience weightlessness and see stunning views of Earth from space. In the future, space tourism could extend to longer trips, even offering stays at space stations or lunar hotels. The dream of human exploration of Mars may soon be within reach. In the future, we may see the creation of space bases or colonies, where travellers can explore new planets and take part into the beginning stages of living on another world. This exciting possibility will be supported by advances in life support systems, the construction of habitats, and using local resources to make sure the ventures are safe and sustainable. As space tourism grows, it will not only open new ways for humans to explore and enjoy space, but it will also spark innovations in technology and create a deeper interest in space science. This brings humanity closer to the dream of becoming a species that lives on multiple planets. Asteroid mining is another fascinating idea, full of promise and challenges. Asteroids are rich in valuable metals like iron, nickel, cobalt, and even precious metals like platinum and gold. These metals are important for industries here on Earth, especially in electronics and renewable energy. Mining asteroids could ease the pressure on Earth's resources and reduce the impact of traditional mining. Some asteroids even contain water, which could be used to fuel future space missions, making space travel more sustainable. While asteroid mining holds a lot of potential, it also comes with risks. Mining in space is a difficult task due to the harsh environment, such as extreme temperatures, radiation, and microgravity. The high cost of space missions adds to the challenge. There are also legal issues surrounding who owns the resources in space and how to avoid damaging the environment around these objects. To make space exploration a success, international collaborations are key. Many countries are coming together to share resources, reduce risks, and make large projects more manageable. For example, the International Space Station (ISS) is a symbol of global teamwork. The space station allows astronauts from different countries to conduct research that benefits everyone. Similarly, the James Webb Space Telescope, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, is helping scientists discover new things about the universe. Working together like this makes it possible to achieve goals that would be too difficult for one country to do alone. Planetary exploration also benefits from these collaborations. For instance, the ExoMars mission, a joint effort between the European Space Agency, ESA, and Russia's Roscosmos, is looking for signs of life on Mars. This teamwork helps ensure that scientists from all over the world can pool their knowledge and resources to explore new frontiers. Meteor showers are another amazing part of the night sky. Every year we see beautiful showers of shooting stars, and some of the best ones occur during the Perseid meteor shower in August. These meteors come from the debris of a comet and can light up the sky with bright flashes, sometimes even showing off fireballs that shine even brighter than the stars around them. The Geminid meteor shower in December is another highlight. Unlike other meteor showers that come from comets, the Geminids are linked to an asteroid. These meteors are known for their slow movement and bright, colourful streaks across the sky. At its peak, the Geminids can produce over 100 meteors an hour, offering a dazzling display to those who brave the chilly December nights. Meteor showers happen when Earth passes through streams of space debris left by comets or asteroids. These small particles, no bigger than sand grains, enter the Earth's atmosphere at high speeds. The friction with the atmosphere causes them to burn up and create bright trails of light across the sky. Each meteor shower is named after the constellation from which it seems to come. For example, the Perseids come from the constellation Perseus, while the Geminids come from Gemini. The predictability of these showers comes from the Earth's yearly journey through the debris trails left by comets or asteroids, ensuring that we see these beautiful sights every year. Auroras, or the northern and southern lights, are another breathtaking natural wonder. These colourful light displays happen when charged particles from the sun interact with Earth's magnetic field and atmosphere. Most of the particles are deflected by Earth's protective shield, but some are funneled toward the poles where the field lines meet. The light shows are caused when these particles collide with the gases in the Earth's upper atmosphere, causing them to glow. The colours we see in auroras depend on the gases they collide with. Oxygen can create green or red light, with green being more common at lower altitudes and red appearing higher up. Nitrogen tends to produce blue or purple red lights. The intensity and beauty of the auroras depend on the sun's activity, such as solar flares or coronal mass ejections, CMEs. During times of high solar activity, auroras are more frequent and can be seen at lower latitudes than usual. These magical light displays often appear as gently waving curtains, spirals, or even bright bursts that change colour and intensity, offering a spectacular and unpredictable show. Draws remind us of the complex relationship between the Sun and the Earth. They show us how everything in our solar system is connected. People in places like Scandinavia, Canada, Alaska and Antarctica are lucky to see amazing natural light shows in the sky like the Northern Lights. These events continue to inspire wonder and curiosity. Cosmic events like eclipses and transits offer some of the most incredible sights visible from Earth. These events catch the attention of both new stargazers and professional astronomers. Solar eclipses are especially remarkable. A solar eclipse happens when the Moon passes between the Earth and the Sun, casting a shadow on our planet. There are different types of solar eclipses: total, partial, and annular. A total solar eclipse, where the Moon fully covers the Sun, is rare and breathtaking. It can turn daytime into darkness and reveal the Sun's glowing outer atmosphere called the corona. These events provide scientists with a chance to study the Sun's atmosphere and improve our understanding of solar phenomena. Lunar eclipses are just as fascinating. A lunar eclipse happens when the Earth blocks sunlight from reaching the Moon, casting a shadow on it. Unlike solar eclipses, lunar eclipses can be seen from anywhere on the dark side of Earth and may last a few hours. A total lunar eclipse, or blood moon, is especially striking, as this moon takes on a deep red colour due to sunlight scattering through the Earth's atmosphere. During these events, scientists can study changes on the Moon's surface, while the public enjoys a captivating spectacle that has intrigued humans for thousands of years. Planetary transits, when a planet passes directly between Earth and the Sun, are also significant events. The most famous transits are those of Mercury and Venus. During these transits, the planet appears as a small dark dot moving across the Sun's surface. These transits are rare, with Mercury transits happening about 13 or 14 times per century, and Venus transits occurring in pairs separated by more than a century. These events are valuable for scientists, helping them refine their understanding of the planet's orbits and measure distances in the solar system. Conjunctions, where two celestial bodies appear close together in the sky, are visually stunning and hold astrological meaning for many cultures. The Great Conjunction of Jupiter and Saturn, which happens every 20 years, is especially noteworthy. During this event, the planets align closely in the sky, creating a beautiful and symbolic display. Each of these cosmic events not only offers beautiful visuals, but also provides important opportunities for scientific research. They allow astronomers to gather data on celestial mechanics, atmospheres, and the properties of solar and planetary systems, bringing both observers and scientists together in shared curiosity about the cosmos. Gamma-ray bursts, GRBs, and other high-energy events have changed our understanding of the universe. GRBs are intense flashes of gamma radiation, the most energetic form of light, lasting from milliseconds to several minutes. They are usually classified into two types: short-duration GRBs, which last less than 2 seconds and likely come from merging neutron stars, and long-duration GRBs, which last longer and are often linked to massive stars collapsing into black holes. The study of GRBs has given us valuable information about the death of stars, the formation of black holes, and the behaviour of matter in extreme conditions. These bursts release more energy in just a few seconds than the Sun will emit over its entire 10 billion year lifespan. This enormous release of energy provides a unique opportunity to study relativistic physics and the formation and movement of jets, which are fast-moving streams of particles created by these extreme events. By observing the afterglows of GRBs in different wavelengths, from X-rays to radio waves, astronomers can learn about the environment around the burst. This helps them study the interstellar medium and even the host galaxy. Other high-energy events, like supernovae and active galactic nuclei, AGN, also help us understand the universe. Supernovae are the explosive deaths of massive stars. They not only spread heavy elements through space, but also serve as cosmic distance markers. Type 1 in supernovae have been crucial in measuring distances and led to the discovery that the universe is expanding at an accelerating rate, which is believed to be caused by dark energy. AGN, powered by supermassive black holes at the centers of galaxies, emit huge amounts of high-energy radiation as they consume matter. Studying AGN has advanced our understanding of black hole growth, galaxy evolution, and the relationship between central black holes and their host galaxies. Observations of AGN in different wavelengths, like gamma rays, X-rays, and radio waves, have helped scientists learn about processes like the movement of matter in accretion disks, the formation of relativistic jets, and the feedback mechanisms that regulate star formation in galaxies. The study of GRBs and other high-energy phenomena has greatly improved our understanding of stellar evolution, black hole physics, galaxy formation, and cosmology. These studies continue to push the boundaries of astrophysics, uncovering the fundamental processes that control the universe and guiding future research in both observational and theoretical fields.